Hello.
I'm going to start first.
Okay.
Okay. All right. Here, you guys, this is your clicker.
Oh, you have a hand.
Okay. Oh my gosh. This is what happens when you've had no sleep. Okay. No. I need to get pictures. Yeah, I just have to take you all seriously now. You look so good. All right, Dustin, let me know. We ready? All right. Good morning. We want to thank you all for being here today, and we're so excited to be celebrating our senior capstones. Today we have both mechanical engineering and our multidisciplinary. Our multidisciplinary will be in the afternoon time, along with the rest of our mechanical engineering capstones. These students have worked really, I won't say hard, they worked very productively in the last 15 weeks, and they're so excited to present to you their product that they've been working on with a client. And I'm very excited to also have both of my other colleagues here who have led Capstone. First off, we have our first group ever from Shady Grove, our extension campus in mechanical engineering, so we're very excited to have them. And so Professor Adam, I'm going to mess up your name, Bredenoff, is that right? Good, okay. And Dr. Paris von Lockett also as well is here, who also led the capstones this semester. Later I will have Dr. LaBerge, who will also be talking about the multidisciplinary capstones. We'd like to thank our American Society of Mechanical Engineers who are here from their professional society, who are here to judge our capstone teams today, and we'll be giving them feedback and taking out of their very busy time in their schedules to be able to be here to see our teams, and also give them all jobs. You're welcome. So with that being said, I'm very excited to present our first group who will be discussing. In fact, I'm just going to let them go ahead and talk. And are you all ready?
Yes.
All right, and I will bring it over here.
Sure. Can we start with
Yeah, and make sure again you're in the all right, and you guys are ready.
Hi, I'm Garvey.
I'm Alejandro.
And I'm Matthew.
This is our Capstone project, which is a automation sortation machine from Shady Grove. So our client is Professor Adam Bredendorf, who is a professor at UMBC. So the goal of this project is to create a automation device that will be used as a learning tool for an upcoming automation elective. For the requirements, we need to develop a system that sorts 3 different materials. In addition to that, we need to it needs to be fully automated with the use of PLCs. So we had several components generously donated for our system, which include a Dubot conveyor belt, a Siemens S7-1200 somatic controller, as well as terminal blocks, wires, and circuit breakers. To get into more detail about the system requirements, it needed to have an actuator, and that could be either electric or pneumatic, as well as the use of sensors, PLC programming, conveyor belt, and it needed to be sorted by color or material.
In terms of our first initial design, first we wanted to get the layout of our system. So that meant doing a sketch where we had our first inductive sensor was going to sense the metallic material or its metallic specimen. Our second sensor was going to be a capacitive sensor that was going to sense a range of materials. And then we would have a container, a round container that would store the specimen that was going to travel in the conveyor. After knowing that, we wanted to see this in a 3D sense, so we went into SolidWorks and just designed a rough draft or a FAR design. Now for our first prototype, we decided to implement, in that previous design, we decided to implement a control arm, which in this control arm, it keeps a distance between the sensors and the specimen that are traveling to. We had 2 side bins and an end bin. The 2 side bins would be for the specimens that are sensed, and the end bin would be for the specimen that is not sensed by either of the sensors. On the second prototype, we then decided to put mounts on the actuator. There will be a rear mount for the actuators and 30 millimeter mounts for the sensors. Now for the final design, going through that, We would have a emergency stop for safety. We would have pneumatic components such as like the directional control valve, our new a new mount for the actuators that would be front mount, and we would have 2 photoelectric sensors, one in the front, one in the back, and we would be keeping the things from our initial design and first prototypes, as well as our on and off switch. Now, going into the pneumatic schematics. And in the pneumatic schematics, we first have our design that would allow for the system of the air to go into it. Then we would have an exhaust valve. This exhaust valve would allow for the regulator to be kept on the same pressure or same PSI, but also, for example, if there's an overload of pressure, we would exhaust it without having to damage the system. Now we would have a flow control valve. So flow control valves do the speed of the system of the actuators, and are spring-loaded directional valves. The directional valves control the movement of the actuators. Last but not least, we have the actuators that are the ones in charge to push the system artifacts into the bins.
And next we have the electrical schematics. On the left side we have the wiring diagram for the PLC inputs, and on the right side we have the wiring diagram for the PLC outputs. As you can see on both diagrams, we have the 24 volt on the left side and 0 volt on the right side. If we primarily look at the wiring diagram for the PLC input, we followed a convention in our system where we used for 24 volts brown wire, and for 0 volts on the PLC inputs we used a mix of, it was white and blue striped wire. And then for our PLC outputs, we followed a convention where for 24 volts, the connection we used is a black wire, and for the 0 volts, we used all yellow wire. And as you can see, we have all of our corresponding inputs and outputs in the correct slots for the PLC.
So the figure on the left depicts the addresses used for our system, which include inputs, outputs, and memory bits. So for our ladder logic, we use the sealant circuit for our system so we can maintain continuity even when a signal was lost. This was used for the conveyor and the sensor. In addition to that, we used a ton timer to account for the distance in between the sensor and the actuator. In other words, when the sensor senses a material, the solenoid valve will be energized after a certain time.
So now we have a budget analysis, which is a summary of our bill of materials, and we have listed general components that we purchased, such as the aluminum base, the pneumatics, the sensors, our 3D filament spool, which we selected PLA since it was the most cost effective, as well as our motors and such. And we came out to a total of right under 1,000, which was our budget. So that worked out perfectly. And next we go into the fabricated parts. So we use the PLA to 3D print 4 parts depicted in this one and 1 on the next slide, starting with the directional arm, which would place the materials that would be sensed within detecting range of the sensors. And then we have the end bin, which would catch the component or material that would reach the end of the system. And then we have the side bin, which would go would catch the components that would be pushed by the actuators on the sides of the system, and the photoelectric mount, which would be used for the photoelectric sensors to detect if the component is in the beginning of the system or if it's passed at the end of the system. And lastly, for the 3D printed part, we have the motor mount, which we designed in order to keep the motor stationary so it wouldn't be rotating for the conveyor. And then we have the aluminum base along with the wooden base. The aluminum base was made from aluminum extrusion, and then the wooden base was attached on top so we could attach our pneumatic components, as well as we cut a hole so we could manage our wires, which would go to the PLC, which would be mounted to the DIN rail underneath.
So here's a brief overview of the timeline of our project, starting with stage 1, the selection of our project, as well as the PLC decision. So we were given the option between Siemens, Allen Bradley, and Click, and we did our initial sensor research as well as ladder logic research. In stage 2, we did our first and second prototype. So in stage 3, we did our selection of specimens for our containers as well as initial assembly of our pneumatic and sensor components. So finally, we went to Blue Ridge Technical College in West Virginia to attend a workshop in which we received expertise in wiring, pneumatics, and PLC programming by Mark Bittner and Dave Teets. We also did our final assembly at the location.
And lastly, we just have a simulation of the system. Right now, we have the metal specimen, which is being sensed by the inductive sensor and being pushed into the corresponding bin. It's sensing the dielectric constant of the metal, which is infinite. And next we have the water specimen, which is going down the line and will be sensed by the capacitive sensor, sensing its dielectric constant of 88 and pushing it to its corresponding bin. And then we have the last specimen, which is just air, going to be sensed by neither the inductive or capacitive, and only be sensed by the photoelectric, making its way all the way to the end. Thank you.
Yeah, can you talk about how you made your choice in deciding your inputs that are going into the PLC?
Or what inputs were going to go into the PLC?
Yeah, how you made that decision in choosing what inputs to include and what not to include?
So for the inputs, we used our sensors as well as, so pretty much it was all of the sensors. And for our outputs, it was the motor as well as the lights that were used for a system.
If I could add to that, the inputs would be things that would input something. So a signal would be inputted into the PLC. So, for example, when there was a sensing of one of the materials, this would be an input to the system, you know, saying, okay, this is a metallic material, so do this such thing, which would be the actuating of the specimen that is going through.
Can you go back, maybe can you go back to the inputs slide?
Sure.
Not that one. There was, yeah. So I see, for example, you have the e-stops there, right? You have a start button, push button, photo eyes. My question is, it didn't seem like an e-stop. I know it's required, but can you discuss just like your process for choosing what inputs you thought were important to include outside of like the sensors and what you chose to leave out of there?
So when this came into that, we needed a start and stop button because we needed sometimes, if we needed the system to stop it at the moment or see the sensing distance in between them, we needed something quick. Rather than having an emergency stop that would finish the whole system, we had something that it would still be running, still thinking in the PLC, rather than just like, okay, you're not doing anything anymore. Then for the others, emergency button, this would needed to be another input that needed to be implemented into it, just in case if we had any wiring problem, because the PLC is very intricate in terms of wiring and voltage going into it. So not having an emergency stop and just pressing the button for start and stop would also mess it up. So with that emergency, we at least had the chance to really stop it and like just turn off the whole system.
It also isn't practical just to turn on the circuit breaker and for the system to start running, which is why we implemented that start and stop. Because in the industry, you see that. So we're trying to mimic almost what you would see in the industry.
Yeah, so when we were doing this, when we went into Blue Ridge Community College, we had this sense of seeing how this would be in, for example, Volvo, or how it would be implemented, how this automation would be implemented in bigger stages, such as in manufacturing.
What about some of your components? Like, why did you choose a pneumatic system pushing versus like just an electric motor? And then how did you choose things like the belt, right? Like, did you choose like a frictionless belt? Like things like that. Can you talk about those decisions? Did you make any thinking into making that selection?
So for our belt, it was donated from us from Dr. Wu. And in terms of the pneumatic components, we selected We selected pneumatics over electric due to the price difference. It was almost 3 times the cost using electric.
More questions could be asked.
Thank you so much, guys.
To the table. So thank you very much.
Thank you.
Great job. That's really hard to be the first group. And then we have our second group come up and we load this presentation. That's correct, yep.
All right, good morning, everybody. Our project is the Thermo Braille display. We're Thrail. My name is Jonathan. On my left, we have Devin, Michael, and Johnny. Bit of background on our project. Our customer is Professor Conacher, and our goal is to create a portable Thermo Braille display. For a bit of background on the project, current portable Braille displays utilize a piezoelectric material, which is fairly expensive. So we aim to create a cheaper alternative while maintaining the key features of connectivity, the proper output, and the user interface. The key requirements for the device are the device shall heat up to a maximum of 50 degrees Celsius, shall heat up a minimum rate of 0.2 degrees Celsius per 5 seconds, which is a minimum temperature difference that can be felt by human fingers, shall cool down a minimum rate of 0.2 degrees Celsius per 20 seconds, shall maintain proportionally sized Braille pixels, shall have a smooth outer surface, and should incorporate keyboard input and should be readable 80% of the time. So for our design evolution, you can see our initial prototype on the right. Our initial heating source was LEDs, but it did not have the heating effect that we'd hoped. We implemented the Arduino, which was coded to test display the letter A, which it did so successfully.
For our second prototype, we decided to test different heating sources to find which one would best fit our criteria. We tested different ceramic heating sources as well as some nichrome wire and some different polyamide heating plates. So these are the results from our tests. We tested which ones had the biggest voltage drop as well as the longest heating time and cooling time. We found that the polyamide heater plates had the best results for the criteria that we had, and we found that they also cooled down quicker if they were fan cooled. So you can see on the right, that's the polyamide heater film that we ended up going with. We ended up rolling it up into a small roll so that it can fit easily against the Braille pixel. On the left, you can see that we decided to use a transistor because the Arduino did not have enough power to send to the heating element, so we decided to use a power supply to send to the heating element, which would be controlled by the Arduino. So for our first model, we decided to get a case for the actual Braille pixels. On the bottom left, you can see that we decided to use copper, small pieces of copper with the heating element up against them, and then we've made enough room on the inside for the different wiring, breadboard, and the Arduino with the fan running through it so that it gets enough cooling. So for the final model, we moved a few things around on the inside for better wiring. We added a safety light just to show when the system is on and off, and we added a port for the power supply to plug into.
So here's the final design that we wound up constructing. As you can see, the actual case itself is made of 3D printed material, and right around the Braille pixels, we use a different material that's more resistant to heat. On the bottom there, you can see how we wound up connecting the polyamide strips to the copper, and here you can see all the internal wiring, and these are the transistors, and these are just indicator lights. So for our plans for testing, we have a thermal camera, which we use to accurately see which Braille dots are being heated up. And then we also use a thermometer to measure and graph the rate of cooling and heating. And we also aim to define and measure power usage of the entire device. And lastly, we conducted a quality test to make sure that we could accurately determine which of the Braille pixels is actually being heated up. So these are some of the thermal camera images. You can see which ones are heating up pretty clearly. And we use it to spell out UMBC, which is, just for fun, pretty cool. So here's our average time versus temperature to heat graph. You can see that it takes about 17 seconds to initialize. We'll get more into that later. And then after that, it's not quite linear, but it heats up at about 1 degree Celsius every 5 seconds, which exceeds the parameter of 0.2 degrees Celsius. And here's our cooling curve, which happens relatively linearly. And it cools at a rate of 0.76 degrees Celsius every 20 seconds, which again exceeds our minimum criteria.
So for our power usage, we illustrate here the time constants used to moderate the heating elements. We start with a 17-second initial duration, which allows the elements to heat up. We then enter into an alternating current series, where we now use to maintain our temperatures so that we're able to keep a steady temp for readability. Next, we had two main facets for our reliability assessment. Mainly, we wanted to assess the difficulty and the success rate with being able to read the individual Braille characters. From that, we found we were able to reach 88%, which was above our minimum criteria of 80% readability. Additionally, we wanted to identify how difficult was it to identify which pixels were actually heated up. Based on that difficulty, we assigned a scale 1 to 10, easy to difficult, and we arrived at 3 out of 10 difficulty, which showed that they were relatively easy to identify. However, they had room for improvement. Our data summary, all of our results came in at or above our set criteria, heating up at 1 degree Celsius per 5 seconds versus 0.2 degrees Celsius per 5 seconds, and cooling down simultaneously better than the 0.2 degrees Celsius per 20 seconds. Our power stayed under what would be required for any wall outlet operated device, which was something we implemented later on as a criteria, and additionally, we saw above an 80% reliability and readability. Here we showed that we came in under budget at $150 versus our $200 set budget. We were very pleased with this, and we can show here that all of our individual components to completely replicate the device. Going forward, we think the most important thing would be implementing a PID controller so that we can properly regulate the character temperatures, and that would additionally add a good factor of safety because heat can be dangerous. We don't want to burn anybody. After that, we would want to decrease the Braille characters because right now we enlarge them for prototype purposes, but we would want to meet current standards. Additionally, improve cooling so that we can get that down to a quicker rate, and we'd want to convert from a breadboard to a PCB to increase reliability and compactness. Our timeline shown here illustrates that from beginning of February to middle of February, we did a lot of background research, and through client research, we were able to lay a groundwork out for defining our project. Next, moving into the middle of March, we started doing our initial hardware assessment and design choices. From there into the middle of April, we did our heating element choices, decisions made to ensure through thorough testing we could find something that met all of our criteria. Into April, we then finalized all of our individual component testings and combined everything. Moving into May, we did our final testing. Here are our references. Thank you so much. Any questions?
So when designing your material for the pixels for your prototype, was there any design process or thinking going into the choice of copper and moving ahead with further prototypes? Is there any thought into either using different materials or looking at how thermal mass plays into your performance?
Yeah, so our initial choice with copper was because we thought it would be one of the most easily and readily available and cheap thermally conductive materials. We really didn't want the heaters to be right in contact with someone's skin because they can heat up unexpectedly quickly and unexpectedly not heat up as much. So we thought using this we would have more control over the constant because we can just do the conduction calculations and ensure that, okay, even if the heater doesn't heat up too much, it's not going to conduct as much through the copper, and we can ensure that the person doesn't get hurt. Going forward, we definitely would want to decrease the copper thickness, and that's an excellent suggestion to look at alternate based on thermal densities.
Additionally, the copper on the top was supposed to be a completely flat surface, so if we put the heating element on the top, it wouldn't be a completely flat surface and be kind of a little more obvious to see the heating element. So that's why we added the copper, or the heating element underneath the copper to better, show a cleaner surface on the top.
And then you had mentioned it's surrounded by a material that's thermally resistant.
Yes.
What material is that, and was it also 3D printed?
Yes, so that material is ABS. It's higher heat resistant than the PLA with the rest of the box. We just used that because that's what we had readily available, but it was able to resist the heat from the actual like copper and heating elements.
And if you go back to our thermal imaging, you can see that the only real bleed effect, thermal bleed effect, is through the gaps between the copper and the material. We don't see a lot of bleed into the material itself.
Mm-hmm. Okay, thank you.
Thank you so much.
Thank you.
Again, you'll be able to have an opportunity to ask more questions later. And just as a reminder to my fabulous students, two things that you actually have a lot of amazing comments coming through YouTube right now, through chat. So if you wanted to go check the live stream, there's a couple of people, I think they're your parents, that are saying very nice stuff. And also to make sure to hold the mic here. What? Ready?
This is the crash protection utility pole. I am JD. This is Brian, Tanner, and Shia. For our background, our customer was Baltimore Gas and Electric. Our goal was to develop a utility pole that reduces the severity of vehicular collision by absorbing energy. And our purpose was to reduce fatalities and injuries as a consequence of utility pole collisions. Some of our key requirements: it shall be designed to reduce force experience by driver, support utilities after collision and through inclement weather, remain resistant to elements, and lastly, the pole shall not protrude 5 inches beyond its current diameter.
So for our evolution, we had 3 prototypes. For our first prototype, we had a general utility pole with 12 sides. That's common with larger utility poles. And around the perimeter, there are 12 plates which will absorb or transfer the impact of a car inwards using those pins. And there will be an energy absorption material that's not modeled, just for clarity, that will actually absorb the material from those pins. The customer didn't like this because it was unsightly, it could be caught on things, and the holes through the utility pole could cause fatigue issues through wind loadings, and it could also lead to water entrapment, which would decrease the lifespan of the pole. So for a second prototype, we decided to create a standalone insert, which was fluid tight. That can be seen in blue, and that would be a bolted connection which would facilitate serviceability. So once the insert was crashed into, it could be replaced relatively easily by installation crews. The customer, when they saw this, they said that they would prefer that it was welded, despite the installation and serviceability concerns. They wanted it to be fluid tight. They didn't want internal fluids or external fluids because the future plans are for there to be a fluid encased in this to further transfer energy. So with that, we decided to implement a fully welded construction with our final prototype. That pole in the middle is what actually withstands the loading from the utilities, the weight of the pole, and will resist the impact of the vehicle. But like I said, there's an insert on the inside that actually absorbs the energy of the impact. For our general design, we utilize existing pole construction, so there are no proprietary pole geometries outside of the crush zone. The crush zone is positioned at bumper level for DOT specifications for bumper height, so 16 to 20 inches above ground level is the center line of our utility pole. The utility pole is supported by a central support post, as I mentioned on the previous slide, and the crush zone is replaceable following collision. Unfortunately, due to the customer's request, that will require grinding and welding of the external skin, but that can be replaced. And it's worth noting that the external skin is significantly thinner than the thickness of the utility pole generally is. That's just to make sure that the energy absorption material stays within and water does not get into the pole.
In terms of energy entering from the car, so based off the crash test done by BG&E of a Honda Accord entering around 35 miles an hour, we have about 210 kilojoules entering the system. And in terms of the energy absorbing material, high density aluminum foam has an energy absorption ability of around 4,000 kilojoules per meter cubed. And then taking into account the volume of our crush zone, we get about 100 kilojoules absorbed, which is about 48% of the energy absorbed by the pole. So for our project, we were not able to construct a full-size transmission pole, but hopefully in the future, full-scale testing would include a full-scale crash test, which would have a data acquisition system on board to record speed, duration of impact, as well as accelerometers to determine the force experienced by the drivers. This also allow us to record deformation of the pole as well as deformation of the vehicle and inspect for any structural issues, as one of the key requirements was to make sure that the pole was structurally sound after the collision. Another test we like to see done was a Sharpie impact test, just accounting for the change in potential energy of the impact tester. This allows us to get a value of the energy absorbed and compare it to our theoretical value.
So for our actual analysis to evaluate the safety of the pole and its ability to withstand the loads of the utilities, the collision, and wind loadings, we conducted FEA analysis. For the wind loading, it is in our area, 75 mile an hour wind gusts is the requirement for transmission poles. So we transferred that, we used calculations available in a handbook that we found and calculated 2,900 pound loading from a 75 mile an hour gust given the dimensions of our pole. We incorporated a 1.25 factor of safety into this just as a buffer and got 3,600 pounds. So we also incorporated a 3,000 pound vertical load to represent the weight of the utilities, and this was derived from a 500 pound load used in the BG&E study. We were worried about that being way too low and different configurations of the pole exceeding that, so we incorporated a factor of safety buffer of 6. And then the 60,000 pound impact loading is representative of the Honda Accord collision and the data determined during that study through impulse momentum calculations. And this resulted in no yield for our system given the material properties.
In order to better conceptualize our project, obviously we didn't make a full-scale pole, but we wanted to produce a 1/8 scale model in order to better showcase our design to the customer. We 3D printed this model on a Prusa XL 3D printer and then machined the aluminum foam to place inside the cylinder. Here's our cost budget for that prototype. We went with really cost-effective materials to speed up production time. We were actually able to produce a full-scale prototype within a week of finalizing the design. And here's a brief timeline of our design. Because we had to fit a design of a large project within a short timeline, we had to really stick to the plan in order not to fall behind. We started by first well-defining the scope in order to make sure that we were meeting all the customers' requirements. Using the prototype 1 and prototype 2 feedback, we were able to make a third prototype that met all the customers' requirements, made them really happy, and here we are now. questions?
Is this designed for, is it supposed to go on any type of pole out there, or is it specific to poles that are of certain material? Because some are made of metal, some are wood.
Right. So the customer initially asked us to do this for 13, 37, and 69 kilovolt utility poles. They later informed us, and we found out that the former two were constructed of wood, which would, you can't, given the ADA restrictions, you can't make the pole any bigger than it is, which means that you have to go inside of the pole. And I mean, it's wood, so you can't really put anything inside of the wooden pole, so we were restricted to the metal poles. And specifically, the customer is looking to implement this in specific locations where collisions are very common.
So with crushing it down low, is there any concern with the extra moment on top, like say like a light pole that's kind of hanging out far, like hitting it low will actually cause it to topple over since there's less area at the bottom?
Right, so we tried to model that during our FEA with our collision, so that 60,000 pound load was the impulse momentum calculation. That was the load exerted by the vehicle on the pole at that level. Testing will have to confirm whether that is accurate or not, but we're very restricted at this point in time.
Great presentation. I kind of wanted to go back to the FEA model. I was wondering what material model you guys use for the carbon foam, and if you guys could expand a little bit more on the limitations of the model and paths forwards to getting a more accurate representation of that impact loading.
Right, so the aluminum foam does not bear any load during static events, so it's only during collisions that that's important. So we use the energy absorption characteristics of that foam strictly to calculate impact energy absorption, but for the actual material properties of the pole, we used 4130 was the center pole, the center material, and then around the 1018 A519 equivalent material was used for the gusseted supports, which are in green there, and the actual utility pole itself.
Thank you.
Congratulations to so far all of our presentations. This is your last one, so this is your final. All right. Yeah, there you go. Yeah. Okay.
Good morning, everyone. I'm Cole Reed.
I'm Sean Bryant.
I'm Alicia Ennels.
And I'm Jonathan Lewis.
And we are the Easy Lift design team. And our customer was Mr. Colin Bonds. A little bit about Mr. Bonds. He is an associate with Clinton Learning Solutions, and they specialize in learning technologies. For our project goal, we wanted to improve the current Easy Lift design to enhance stability and to optimize it for single operator use. Some customer requirements: they wanted to increase the stability of the current lift when installing TVs on walls. They don't want the lift to top or tip when installing, and they wanted to enable it for single person use. That way they can optimize their output by installing more displays per day. Some quantifiable requirements: they wanted the lift to support a 200-pound weight capacity, a minimum of 40 inches off the ground. They needed to lift the display. They wanted to support a maximum of 86-inch displays. That's corner to corner for your displays. They wanted to get the display within 3 inches of the wall, and it had to fit through an 80 by 36-inch door frame.
For prototype 1, our initial idea was to improve the stability by making the base steel and also creating a triangular telescoping leg orientation. It was also pivoting that would allow for a greater stability triangle for larger displays. However, through FEA analysis, we quickly realized that there would be stress concentrations at the bolts and wheel arm connections. So for prototype 2, we aim to mitigate these issues by increasing the stiffness through a square channel at the base. We also added threaded cylindrical wheel arm connections. However, due to the complicated fabrication of this, it would be more expensive and it would be harder over time for operators to replace wheels if necessary. So this prompted a redesign that led us to simplifying it by removing the threaded cylindrical connections and the telescoping legs, as it was an unnecessary feature that would cause more expensive and intricate manufacturing process. We also added additional wheels in the front and changed the entire base, the entire lift to be comprised of only aluminum. For our final design, as I mentioned, the entire lift is aluminum. This is both lightweight, as the operator has to lift this themselves and transport it into their vehicle. It also has 4 locking wheels in the front with 6 total. This will prevent any slippage or rolling while the lift is getting installed. And it has a 4-component disassembly, again for ease of transport, as operators have to load this into the back of vans and work trucks alike. Finally, there are hooks for nylon straps that will secure the display when it is mounted onto the tray, as you can see.
For our final design, we have our stresses on our tray and base due to our point loads acting on our system. From this, we can see that there's no areas of high stress on our system. Will we confirm this with our bolt calculations? Our bolt calculations, as well as our force for separation, can be seen here, as well as our factor of safety at the bottom of 1.7, which is greater than our limit of 1.5. Lastly, another area of improvement we saw was our deflection. We saw our deflection see a 96.9% reduction compared to our original base. This can be attributed to our square channeling at the bottom of the base that we added, as well as moving our legs closer to the point load in the center.
So for before we bought any parts for our lift, we wanted to build a prototype, test it out and see what we can learn from it. This prototype was built completely out of wood, and we utilized a 100-pound display that our customer provided us with, and these are the results. That prototype was able to lift that 100-pound display 42 inches from the ground and also come flush to a wall. Because those met some of our requirements, we were happy with this result, and we moved on to fabrication. Our customer also provided us with one of their lifts of their own and let us use it however we saw fit. So we reused most of their parts for our final build, such as the 2 shafts, the lifting mechanism, and the flat base plate. And for the parts that we redesigned, the plan was for us to send our CAD files and our engineering drawings to our customer, for them to send to their manufacturer. They'll make the parts, send it back to us, and we'll build the lift. Unfortunately, things didn't work out, and they weren't able to get the parts back to us, so we had to do, so as a team, we had to buy all the parts ourselves, and we fabricated it on our own.
So our budget breakdown, with the $200 the university allocated us, we came well below that with only $92 spent, with our most expensive item being that aluminum base we constructed. Our testing methods, in order to make sure the lift met our requirements, we would apply a 200-pound load. We would lift that load a minimum of 40 inches off the ground. We would only allow one person to perform a mock install. We would push the lift with the loaded display through an 80 by 36 inch door frame, and we would try to get that lift with the loaded display 3 inches to the wall.
So our customer was unable to provide us with one of their 200-pound displays, so we did all our testing with 220 pounds worth of concrete. And also, when we did this testing, we did it when our legs were at their maximum pivot angle. The reason we did that is because at that angle, that's when the area of the base is the smallest. So here are the results. The lift was able to lift 220 pounds, 54 inches into the air. That 54 is not the maximum. The reason that we stopped at 54 is because when lifting 220 pounds of concrete nearly 5 feet in the air, it's kind of frightening when you know that you're lifting till it tips over. So we just stopped at our 54. This testing was done by a single operator, and this lift is able to roll through your standard door size and come flush to a wall.
So our project timeline ended up being the month of February. We were determining our system requirements. Going into March, we were formulating our concept ideas, creating prototypes 1 and 2, and then testing those through our CAD modeling. Going into April, we determined our final prototype concept, and then through, again, testing those values, FEA through CAD on our final design. Getting towards the end of April, we were assembling our physical prototype of wood, doing some testing and validation on that. And coming to the end of April, we finished up our final design and assembly and testing and validation. Any questions?
How much does the device with modifications weigh?
It weighs about 50 pounds. It's fully constructed, it weighs about 50 pounds, but with that 4-part assembly, you can deconstruct it into 4 separate parts. That way it's more easily loadable into vehicles, and it's less weight when fully transporting the fully constructed lift.
Gotcha. So at the end, you mentioned something very important, which is the tipping point, right? Yep. So now in terms of when someone's operating this, so as you know, I guess it's only designed for displays that are gonna match that base, right? The width of that setting. Do you have, is there anything or any improvements you think you can make to prevent someone from either raising it beyond that tipping point or putting something on there that is, that has a center of gravity that is further out, which could just make the whole thing tip over?
So actually, one of our goals is to have just simply a sticker on there that indicates the load capacity for the operators, so they know that it was built. Even though our testing capacity was 220 pounds, we're still going to stick with the 200-pound requirement. So we want to put a sticker on there that just says that's the maximum capacity. We also talked with our client in terms of the widths of the different displays they have to figure out if that would cause an issue if there were different widths of it. And this was done, the design of this, for the maximum width and the worst case scenario, as you would say. And the straps also are going to help keep that center of gravity close to the center of the lift, so the display isn't just wobbling back and forth.
What were your considerations for going over different surfaces or thresholds or other obstacles?
So the primary use of this is in classroom and educational settings. So most of the flooring they're going to be rolling over is like vinyl flooring, kind of like what we have here, and maybe some carpeted. So based off of the current design, when you're rolling it, it is like kind of wobbly and shaky. But the idea is that once it's loaded, that weight will kind of prevent it from shaking some as much. And also it wasn't an issue when we did testing. And again, the only flooring we really considered was for indoor settings mostly. It's not really advisable that they transport this like outside on asphalt or concrete, because there's unknown obstacles that we can't really predict for them. So the goal is to have them unload it from the van, load it in the educational facility they're installing the lift through, and then transport it throughout the hallways that way. Only for them taking the lift outside of their van or work truck and then moving it inside to the facility. When the operators are installing, they bring this lift with them to each job site, and then they load the display onto it. So there is the outside to inside transition for that, but in terms of the display actually being loaded, it will not be transported from outside to inside.
Thank you very much. Great job. Thank you. Shut down. All right, and our next group here, you want to?
Where's the clicker? So is it just this button?
Yep, that's it.
Good morning, everyone. We're Group 7, Riptide Tech. I'm Brian Davinsky, and to my left is Gabe Cabanilas, Angela Zhang, and Joshua Mosquez. And our project is a small-scale, low-cost wave flume. So for the background of our project, our client is Dr. Brian Ritz, who is an aerospace engineer at the Naval Air Warfare Center in China Lake, California. His problem is that he wants a wave flume for his lab, which is essentially a channel-shaped tank of water with a mechanical paddle used to simulate different types of waves, and he wants to use this for concept design testing and simulation of different sea state conditions. However, commercial wave flumes are too large and expensive. Therefore, our goal is to design but not build a small-scale modular wave flume for him. For some of our key requirements, the wave flume needs to be storable in an 8x3x6 space. It must utilize a wave absorber that can minimize weight deflection during test. It must not require complex fabrication for the assembly beyond the use of basic hand tools. It must be able to simulate scaled up to sea state 5 conditions. It must utilize a motor that is programmable and controllable so that the client can change the wave characteristics during test. And it must stay within a budget of $3,000. So in order to determine some of the requirements for our materials, we constructed a prototype out of plywood and using a plastic sheet to prevent leakage in the water. And we utilized a wood board with a dowel attached to a hinge to simulate the paddle movement. Using this, we were able to experimentally determine some of our requirements, notably including the tank dimensions of our final design, as well as the wave absorber type and angle, and the desired paddle movement to generate the waves, as well as the required paddle displacement and motor specifications for our sea state requirements.
So to design to meet our specifications and requirements, we needed to do some analysis and calculations on each of the subsystems of the wave flume. For our wave generator, we performed an experiment using our prototype to collect data and find a relationship between actual wave heights and linear actuator stroke. We fed this through an equation relating wave period to wave height, which is based on published data of real-life full-scale ocean waves. This allowed us to find some actuator speeds and the paddle's angular displacement. Once graphed, we can get a linear regression in order to project this data up to the full range of sea state 1 through 5 conditions. And then we were able to find the required paddle displacement and the motor specifications in order to generate those sea state 1 through 5 wave heights and periods. For our wave tank, we went with a cast acrylic construction, and in order to determine the thickness of the acrylic sheets, we used a published calculator where we entered the dimensions of our tank that we found in our prototype, which is a 96 by 18 by 18 inch tank. This gave us a minimum thickness of 3/4 of an inch for an open tank design, and then 1/2 an inch thickness for a braced tank design. Our first iteration was that open face design, but during our prototype testing and from some displacement FEA analysis, we found that the open tank gave a deflection of 1/8 of an inch, but the brace design gives us a deflection of about a 1/28 of an inch. So we went with a brace design, and then for added precaution, we made the thickness 3/4 of an inch. For our base analysis, our client specified that we elevate the tank up to about waist height for ease of use during testing. The weight of the water inside the tank at a depth of 12 inches and the weight of the acrylic itself totals about 800 pounds. So in our first iteration, we designed essentially a frame of 2x4s, but during discussions, we were worried about potential horizontal forces and overall strength. So we added plywood sheathing on all 4 sides of the base, which brought up our factor of safety and improved the overall rigidity of the base.
So wave absorption can be improved by either making changes to surface permeability or the slope profile. In our experimental process, we correlated the reflectivity to our settling times and found that lower slope angles can be related to lower settling times. Introducing a foam surface to our system, we were able to further reduce this value by about 2 to 3 seconds. This is our final CAD model along with some fabrication details. Our wave generator is going to be made of stainless steel hardware. It will be a 4-bar linkage connecting together our NEMA 34 stepper motor to our acrylic paddle. Our wave tank will be sheets of cast acrylic that will be bonded together with a solvent cement, and you can also see here the 2x4 bracings supporting the center of the wave film. Our base, on the other hand, will also be made of 2x4s. It will have plywood sheeting for support and will be fastened together with construction and pocket screws. And lastly, for our wave absorber, it will be a polyurethane foam slope with cast acrylic support.
Because our client is in California and he's doing the fabrication, we're not doing any post-fabrication testing, so we have to verify all our specifications beforehand. So for storage, our dimensions fit inside that storage requirement, except for the motor. It sticks out a little above that 8 feet, but it is easily disassembled. For the wave absorber, we found in our prototype testing that we had a 2 to 3 foot test section where basically no wave reflection was recorded. For the assembly, we will provide assembly instructions. For the C-state conditions, we found that torque calculation for the required paddle displacement that we found during our prototype testing. For controllability, we selected controllable components such as the stepper motor and Arduino. And for the budget, we created a bill of materials and also supplied him with cage codes. If you don't know what cage codes are, they're basically a 5-digit combination that allows suppliers to be bought from the government. That allows the government to buy from that supplier. So this is our budget. It is under that $3,000. Most of it coming from that wave tank and wave generator. This also includes shipping. And for our timeline, we spent the beginning researching existing wave flumes, started brainstorming glass, acrylic, wood, plunger, translation paddle, and then we came up with our conceptual design and made our prototypes. We took all of those results and made a lot of adjustments, started formulating our bill of materials until we finalized our design. And the last thing we need to do is to show Dr. Ritz our assembly instructions. Any questions?
Could you talk about the selection of your motor or the actuator and what is its expected lifespan when it's actually being used? Do you know how it's going to be used and what kind of waves are going to be generating? And is that going to be, did you do any analysis on that entire linkage to see how does it work? How does it perform?
Yeah, initially we wanted to go with a linear actuator for simplicity, but we couldn't find any actuators that could meet our specifications, so the speed was much larger than any commercial linear actuators. So we decided to go with that 4-bar linkage and motor, since the motor can meet those speeds, but also it moves all the electronics outside of the tank. So the motor, you saw it was mounted behind the tank, and then the linkage attaches to the top of the paddle. That way all the electronics are out of the water.
I love the mechanism, by the way, in the CAD model. It's awesome. Going back to the FEA model, I saw that you guys returned really high factors of safety. So I was wondering what considerations you might have further on to improve the design to maybe bring those factors of safety down to kind of fit better within the constraints of the project.
So with our design, we thought it was better to just overbuild since we have such a generous budget that allows us to go that far. Our factor safety numbers are really just to validate our design decisions, and most changes between the iterations were just client requested.
Thank you.
Thank you very much. Congratulations. Great job. All right, there you go. Cool guys. You're so cool.
Just click on it.
Yep.
Good morning, everybody. My name is Zachary Taylor. With me is Brant Smith, Darren Taylor, and Joe Puchek, and we are giving our founding presentation for Capstone. We are the electromagnificent cool guys, which you'll see why in a second. So our client is Dr. Paris von Lockett, professor of mechanical engineering here at UMBC, and he does research with magnets, one of which we'll be using for our capstone, shown here on the bottom left. So he tasked us with designing a heat exchanger for this electromagnet, which will stay in his lab. He does research in the middle of the magnet, in between the coils, but the magnet uses 10 kilowatts of power, which is a lot. It produces a lot of heat. So we want to lower that heat for two reasons. One of which is safety. You don't want to be walking around such a massive heat source. And the other reason is when you heat up electrical wire, the resistance goes up, which will weaken the magnetic field. So by cooling it down, by creating a heat exchanger for it, we would not only make it a safer magnet, but we will also strengthen the magnetic field for Dr. von Lockett's research. Some of the requirements he gave us was a budget of $700, just so that we could build it ourselves, produce it, have it finished for him by the time the semester ends in the 15 weeks. And then the big and most important requirement was that it was leakage free, because we wanted to make sure that with so much power going into this magnet, there was no way that any water or any other fluid could go out and possibly severely hurt whoever was using it. And we didn't want to affect the efficiency of the heat exchanger itself. The goal was to dissipate a minimum of 5 kilowatts of heat, but this is in kind of like an optimization problem. We want to dissipate as much as we possibly can within our requirements. We cannot obstruct that experiment zone within the center of the magnet, and we wanted the max temperature of the coils to remain below 120 degrees Fahrenheit.
So over the course of the project, as you can see, our design was continually refined in order to meet our system requirements. So with our first prototype, as you can see on the left, we utilized the 2 enclosure design in order to accommodate the copper coiling on either side of the electromagnet. And these would each be filled with water, which would remain relatively stationary. But what we found with this design was that it presented a significant risk of leakages. So with our second prototype in the center there, we used a single enclosure design, which effectively eliminated any potential leaks. And we also introduced 2 submersible pumps there, which would introduce turbulence into the system to facilitate convective heat transfer. With our final design, which resembles our second prototype, we implemented more powerful submersible pumps, which we felt were more appropriate. And additionally, we modified the design of the enclosure there in order to accommodate the water pressure it would be experiencing and minimize deflections. As you can see with the photograph on the right, the group was successful in fabricating the finalized design from the model. The group refers to this as a double heat exchanger because the copper tubing there surrounds the copper coils in a helical fashion while remaining submerged in a water bath, which is, turbulent as a result of the submersible pumps. And basically how that works is the industrial sized chiller rated at 10.5 kilowatts of heat capacity will circulate coolant first through the vinyl tubing toward the bottom and then into the copper tubing, where it will extract heat from the warm water surrounding the coils. And then after passing through the system, that heated coolant will then return to the chiller to be recooled, and the process will begin over again.
In terms of fabrication, we reused our prototypes, what we used for them. So we first got the copper. This was for prototype 2. It was 2 pieces of 20-foot, 3/8 inch copper tubing. We decided 3/8 because 3/8 is, you can use that by hand, you can bend it easily. Anything bigger, you're not gonna be able to bend by hand. You're gonna have to use tools and you can't make that helical structure. So we took those 2 pieces, made the helical structure by using a 4-inch PVC pipe and just wrapping it around until we got those helical structures. We also were able to connect to the chiller just with brass fittings from a master car, glued them together with pipe glue and pipe tape, and we got those fittings good. We also used that for the vinyl that connects to the copper. And then for the structure, the encasement, we 3D printed that because we had some odd geometry. We thought about epoxy, that didn't work. You can see here we tested a small enclosure of 4 pieces. Here's 1 piece of it. We had to go 4 pieces too because the 3D printers we had available were we couldn't make a structure as big as it is. The structure is very large. So we took 4 pieces, glued them together, and made the enclosure. And then the pumps and thermocouples, as well as the lid, those were the finer decisions, finer stuff that was bought, and those just go right in the enclosure. As for testing, when we first, like for prototype 2, when we first got the copper, we ran water through it, made sure it was leak-free. We had like paper towels under it to make sure that it didn't leak. We were successful, no leaks. We ran plenty of simulations, including CFDs and FEAs. The CFDs have us around, I want to say, 90 degrees, so easily within the 120 degrees that we were looking for. And we also did the FEAs to make sure the structure of the box we were making could withstand the water and the heavy magnet.
As mentioned in our system requirements, our budget was $700. The left column there, we have materials and components that we purchased and the corresponding price. And this totaled to a little bit over $500, which was well below the budget. We were also lucky enough to have some donated materials, such as PLA filament and acrylic sheet, etc. And including these donating materials, we estimated about that it would have cost about $660. And this is our timeline. After defining the system requirements and specifications, we brainstormed some general concept ideas, and we used numerical methods to pick one design concept to pursue. We then created some preliminary CAD models and ran fluid simulations to see the temperature distribution throughout the models. We also went back and tweaked and improved these models to get more favorable results. And then we went to fabricating things like the enclosure and purchasing some of the last parts we needed for assembly, which we then put together and assembled our entire design. As mentioned, we're looking to test it under, at first, a low power source of 1.8 kilowatts, and we're going to check the data with the results of our fluid sims. And then hopefully, if the chiller and the power source is connected, we'll be able to test it under 10 kilowatts. Thank you. Any questions?
I really enjoyed this. Reminds me of some of the work I do. So I saw that you had a kind of a parallel flow path for your chilling fluid. Did you monitor the temperature on each individual coil, and did you see any difference or any difference between the two temperatures between the two coils?
No, we did test it like individually, like one sort of side at a time, but just due to the symmetry of everything, we're sort of assuming that there aren't going to be differences in flow rate or temperature distributions over those copper coils. So.
I want to say the temperature of the water going in or the coolant going in and going out, I think we did, was that part of the CFD, I believe. I want to say it was like 20 degrees difference or something along those lines.
Overall, for the drop?
From the inlet to the outlet, yes,
Okay.
of the copper tubing.
I'm sorry.
Yeah.
Oh, no, actually, that
Okay.
actually captured what I was
Okay.
asking, so. All right, thank you.
So for your enclosure that was 3D printed, what material did you choose? Because some 3D prints can have issues with extra heat on them.
Yeah, that was PLA just because it was donated. That was free. From the simulations, it should not be an issue with heat. It should be totally fine. Glued together, it's holding the magnet up fine. We don't see any issues with that. Yeah, the melting point of PLA is upwards of close to 200 degrees Celsius, and our design, even if it didn't work, it would stop as soon as it gets close to 120 or higher. So we have no issue with the plastic melting.
I mean, most of the heat is concentrated directly around the copper coils and also in the gap between the scrap metal of like the cast iron electromagnet and those coils. So it doesn't really reach, I guess, to the edges of say the enclosure. So it's dissipated, I guess, before it reaches that.
Great. Congratulations. Oops. Let me know that. Maybe.
Good morning, everyone. My name is Malcolm Autry. To my right is Michael Colgan, and to my left is Charlie Morgan and Thomas Song. We are Amino Fusion Forge, and today we're here to present to you all our amino acid capstone project. So we were tasked with creating 25 physical amino acid models that are able to connect to each other and form proteins. And we decided to do this by 3D printing 25 main backbone pieces that are able to connect to 25 different types of 3D printed R side chains in order to create varying models, just like amino acids, with our main audience being researchers and students who are studying proteins, and our clients who taught us about amino acids being Dr. Stephen Freeland, a professor of biology here at UMBC, Ms. Valerie Zhou, a graduate researcher who does biological lab work with Dr. Freeland, and Mr. Sean Brown, a doctorate candidate who also does biological lab work with Dr. Freeland. So we wanted our models to meet the following parameters. We wanted them to be able to rotate 360 degrees along the joints. We wanted them to be able to assemble within 5 minutes. And then when they're connected to each other, we wanted them to be able to withstand their structural integrity. We also wanted them to be able to withstand a load of 90 kilograms. We also wanted them to be able to be made under a budget of $500. We wanted them to be color-coded and labeled correctly. And lastly, we wanted to make sure that the mass production of them is very simple.
For initial design, we pay attention to two components, the joint and the atom itself. For the first prototype, you can see in the top, we want to see what kind of diameter and pin depth we needed. For diameter, we settled on a 4.9 millimeter, and then a pin depth, we want to focus on a 6.4 millimeter. Next would be what kind of material we'll be using. We went with SLA resin initially for its high quality. However, when we printed it on the second prototype, we found that you can only print 100% infill, which drove up the cost, it drove up the density, thus drove up the weight. We then used the reference atom to be carbon, and we set that at 2.2 centimeters. However, you can see in the second prototype that was too small, it did not allow for multiple pin insertion, which is not good, especially for the alpha carbon. We then wanted center bond length to be 1 angstrom to 1 centimeter. For our final design, we ended up going with PLA and FDM for its low cost and its ability to change infill pattern, which in our case we want 15%. That would reduce the weight. We then upscaled the carbon atom from 2.2 to 3.5 centimeters. And then because we upscaled the carbon atom, we had to upscale the bond length. So we did a quick ratio analysis. We did 3.5 divided by 2.2 to get us a new 1.591 centimeters. We still stuck with the Lego black friction pin. However, we changed the diameters of each part. For the alpha carbon, we set that as a press fit 4.7 millimeters. For the other diameters, we set for 4.8 millimeters with a pin depth of 6.1 millimeters. To create the actual model itself, we started with Avogadro, which is a biochemical software that allows you to create different peptides and model different amino acids. But more important for our case, it can provide atom and bond data. There's two ways we went from Avogadro to SolidWorks. Both yield the exact same model. First being the bond length and angles. That's when you made the outline of the shape of SolidWorks, and you input the measurements provided in Avogadro. Second would be a Cartesian coordinate system, where you would take the XYZ locations of each atom and put them in the SolidWorks. To create the actual atom itself, at each point, we create a sphere about that point with the diameter that we needed.
So after we completed each of our components in SolidWorks, we were able to convert the files into STL file types, which allows us to upload to a 3D printing software. In our case, we use Creality Slicer as shown in the top left, which allows us to adjust our infill percentage to 15%, our infill pattern to be cubic, as well as adjust the orientation of our final prints as shown in the top left image. We went through 2 different manufacturers in order to print our components. First of which was University of Maryland's 3D printing lab, where we printed our R side chains, which was 25 components in gray PLA filament, as shown in the top right. Additionally, we did in-house printing with one of our team members' printers, where we printed 25 alpha carbons in black, 25 peptide bonds in blue, 1 amino terminus in orange, and 1 carboxyl terminus in red, as shown on the bottom. Moving forward, for the manufacturing time for both of the manufacturers is around 3 weeks for both orders, so doing them at the same time cut our manufacturing time in half by doing them simultaneously. The main difference between the 2 manufacturers was the cost for printing. So University of Maryland accounts for labor costs. So it was around $102 to print all of our R side chains, or around 10 cents a gram, compared to our in-house manufacturing, which was around $21 or around 3 cents a gram for our parts. The quality across both manufacturers was fantastic. However, the main problem we ran into across both manufacturers was the safe and effective removal of support structures. So in the top right, you can see the method that we use to remove the support structures involves sharp tools and prying off material that's not added onto our final model. If you're not careful, you can either slip and hurt yourself, or you can damage the components as seen in the bottom right if you're not careful. After we have all of our completed components, we were then able to test and verify our specifications, with the main three being joint rotation and locking, atomic ratio accuracy, and compressive loading. So for joint rotation and locking, we wanted to ensure that each of our components was able to be oriented by the user in a set position for up to a 12-mer, which is 12 our side chains, 12 gray components as shown on the left-hand side, and one giant chain. This passed. Additionally, we wanted our atomic ratio accuracy to be consistent throughout our entire model. So a carbon in one component should be 3.5 centimeters, as well as all the other components as well. This also passed for our components. Lastly, for our compressive loading specimens, we wanted to test to see the compressive strength in case someone steps on the component on accident. We simulated this with a 90 kilogram load, and this passed for 80% of our components, with a failure being due to a unique geometry which was approved by our client.
So for timeline, there were 4 phases. Phase 1 was brainstorming. We researched the amino acids, familiarized ourselves with the Avogadro and the new software introduced by their clients, and most importantly, determine what connector we are going to use. And we determined Lego connector pins, and we really modeled our design around those Lego connector pins. Phase 2, into CAD, we distributed the amino acids so we could start CADing, and as if we were subcontracting in-house. Phase 3, we would produce prototypes, and we would take the prototypes to the compressor testing machine to compress and use that data for our final designs, what material, the input percentage, and even the whole diameter for the Lego connector pins were modified accordingly. And we finalized designs early so we can send out the orders to our printers, and that was necessary to give them plenty of time to print. Phase 4, quality control, self-explanatory. We would gather all our final prints, and we thoroughly examine each and every one of them to make sure they meet our quality standards. So if they do not, we have time to go back and reprint. And finally, our budget. The mechanical engineering department allocated us an additional $200, and our client, Dr. Freeland, personally added $300. Fortunately for him, we stayed within the $200 budget limit at $199, so his wallet can be very grateful. Thank you for your time. Questions?
So I believe I judged something similar to this about 2 semesters ago. What lessons learned did you guys find, and what have you done differently?
So I believe there was two different iterations with that previous project. The first project was done a while ago, and that was they used SLA. And we really like that. That's why we originally went with SLA. In the second project, they found that the scaling was way off in each atom. So one hydrogen on one part would be completely different than the second part. So we went into this mindset saying, all right, what do we like about both options? We like the scaling for the first one. We also like the SLA. We went with the second one. We liked how it looked. However, we had to do different pros and cons with both ones, and we basically pulled both lessons we learned from both. So yeah.
Additionally, one of the main concerns with the previous presentation, or the previous models, was the pin connection method. So one of them used a rubber stopper in between, and another one used PLA against PLA. Both of these methods made the model not retain its shape for longer chains. So a longer chain beyond this for the first 2 models wasn't able to support the structure that the researcher would want to orient. Using the Lego friction pins with a more fixed positioning was another lesson that we learned to apply to our final product as well.
I see that you guys had some difficulty with the support material. Did you guys ever play around with maybe using a dual material print, maybe using polycarbonate under the PLA to break it off easier?
We considered a bunch of different materials, including PETG, stereolithography, and our client made it clear to us when we first started the project that we're focusing more on accessibility with anyone with a 3D printer being able to manufacture this component. So more focusing on the design process, getting the models to be in an SLA format that anyone can print on their 3D printers. For example, University of Maryland used a Prussian Mark IIIS, and we used an Ender 3 Pro, and the quality across both of them was consistent. So this was more of a focus on our design to focus on repeatability and accessibility.
Perfect. Thank you.
Good morning. We are the Oyster location team. I'm Joey, that's Ben, and that is Daniel. Our customer is Dr. Topolewski and the Hollywood Oyster Company. For our background, Hollywood Oyster Company requests that we design a crane system to lift oyster cages out of a hole that is located in the center of a pontoon boat. Requirements for our design is a full CAD model of the crane and a complete list of materials to give to the company. The crane must achieve being able to lift the cage without tipping the boat and lift a maximum of 400 pounds, as well as place the cage anywhere on the deck of the 20-foot pontoon boat. This is their current design. Problems with this current design is that when they lift the cage, it tips the boat, and there's a limited range of places to put the cages on the boat after lifting them up. For our design evolution, our original design had the cross beam and the side beam as I-beams, and the bracket would run use the flanges on the I-beam as a track for the brackets to run. We found there was a lot of stress on the connection between the bracket and the center beam, and that the friction on top of the side beam was too high as well. So we landed on our final design, which has the I-beam or the center beam and the bracket on top of the side beams, and we were able to cut the cost by changing the side beams from I-beams to just aluminum bars. So this is the full design. The two-dimensional gantry crane spans the length and the width of the entire boat. There's a trolley on the center beam that is able to slide from one side of the center beam to the other and is used to hoist the cages out of the boat. And then the bracket and wheel system moves along the side beams the entire length of the boat.
Trust us, it moves. So for actually designing the beams, as we mentioned earlier, the center beam is an I-beam still, not just for strength purposes, but also to provide the flanges for the hoist and the trolley to run the length of it. The side beams are no longer I-beams, they're just flat plates instead, and while that does lower the strength of them, it provides a flat surface for the wheels to run along. Though, since we're on the water, the wheels will be in constant motion, so we also have to machine in divots to act as stopping points. So when the workers are raising or lowering the cage, they don't have to contend with the center beam moving. So the bracket system prevents the center beam from rotating off of the side beams by overhanging on the side beams there. Each bracket has 2 rows of wheels to prevent the beam from tipping either forwards or backwards, and the beam is bolted to the bracket. So within the bracket system, we have the wheel and axle system. The wheels are polyurethane. Not only are they much stronger than we require, but they also have a low height to diameter ratio for the axle. Since the axle diameter is fixed by the stresses we're incurring, having the wheels with a lower height to diameter ratio allows for a shorter bracket, which again is good for preventing tipping. Most of the parts, the beams and the axles, and you'll see on the next slide the bolts, are constructed of alloyed aluminum for corrosion resistance. And in addition, they're given an epoxy coating. Since we're working in an outdoor saltwater environment, degradation of the materials is a large concern.
And the bearings on the axles here are going to be acetal plastic, and they're roller bearings rather than ball bearings, since a majority of the time the loads they're experiencing are static rather than dynamic. Roller bearings distributes the force better than ball bearings and prevents deformation. And lastly, we have all the bolts. 2 different kinds. The shorter ones connect the I-beam in the center to the bracket, and the longer ones are for connections between the side beams and the support beams. The bolts mentioned earlier and all of the associated washers and nuts are constructed of alloyed aluminum.
The trolley is an integral part to this system because it rolls along the flanges of the I-beams and allows the cage and its containments to roll laterally across the crane system. This is going to be made out of steel, not aluminum, because of its readily available and its strength. It'll be able to hold the weight that we've projected it'll need to hold. To counteract for it being steel in a brackage environment, we'll be covering it in that same epoxy weather-resistant coating that the rest of the crane is covered in. The hoist we're using is going to be a 110-volt hoist. We found that it can lift that 400-pound weight at a rate of 1/2 foot per second. That's going to allow the oyster farmers to do what they need to do throughout the day and not impede them by going too slowly. It's going to be powered by a 1,000 watt-hour battery, which we found will allow for 20 lifts and lowerings of these 400-pound cages, which should be adequate for their daily usage. Attached to the hoist will be a 3/8 of an inch nylon rope. We chose this because it's weather and saltwater resistant and can also hold that 400-pound weight that we need it to hold and handle shock loads as well as tensional loads. Since our project was mostly a design concept, our testing was FEA. We found that the maximum load that our aluminum side beams will face is about 2 kilonewtons. So when putting this load on the middle of a side beam, we found that the stress is limited and the deflection is about 0.15 of a centimeter, meaning that it'll be able to hold the weight that we need it to hold pretty reliably. The aluminum center beam is another piece that we had to test. It's going to be holding that same 2,000 newtons of force, and we found that it'll only deflect about 0.2 of a millimeter, meaning that it can hold that force reliably and stably. This final part is our final parts list. This is part of our package that we'll be delivering to our customer and Dr. T. It shows each item, the quantity of items that we need, where we can find the items, and approximately how much it'll cost. The entire cost for this system will be about $7,000, but this does not include labor for setting up the system and putting it together, or transportation for materials to the oyster farm. This slide contains our completed tasks, which are things that we've done throughout the semester. We've established requirements, set specifications according to the oyster company. We've conducted preliminary static analysis. We've done our general design, and based on that, we did additional static analysis and FEA. After we finalized our design, we chose materials, and in the upcoming weeks, we will implement changes based on feedback that we get today and validate and present our project to our customer. We appreciate your time and welcome any questions.
Can you go back to your FEA slides and then your main design? Okay, so you have FEA on the side supports, you have FEA on the I-beam. What about on the roller supporting the I-beam?
Yes, so yeah, we did FEA on that and found pretty much the same result. We, using this information, we chose wood instead of aluminum to cut costs because that was one of the main concerns that we had. We did show very limited deflection, and the stress that we put on the loads was vertical, so the wood didn't have any buckling issues as well.
Okay, can you go back one more slide, or this left more? Left more. Keep going. I just wanted to look at your final design.
Oh, gotcha.
Yeah. Is your design inclusive also of the vertical supports as well?
Sorry?
Is your design inclusive of the vertical supports?
Yes, yeah, those are part of our design as well.
Okay, and you've analyzed those as well and made sure?
Correct, yes.
What about the sway of the sway? Like, especially when you're on a boat and it's rocking?
So yeah, that was one of the reasons that we've had the load being lifted from the center of the boat. One of the issues that they had was they were lifting it off the side, which would cause a lot of sway. But we minimized that by lifting it through a hole in the center of the boat instead of off the sides.
So how can you prevent those? So I understand the load is going to be vertical, but even if the operator is like lifting it, especially with the lifting mechanism, which is a rope, it can sway side to side, right?
Yes.
How much loading have you kind of thought about? Okay, the loading that's going to be side to side, lateral loading, and then which is going to be affecting that rolling mechanism you have on the side channels. What is going to prevent that from tipping or rolling off?
So another reason that we have the vertical side beams as low as we do is to keep the moment of inertia as low as possible so that the tipping is as low as possible. The exact height of this is about 5'5", I believe. So and it'll also be on a pretty big boat, which has a lot of lower held mass. So that's what we're accounting for to reduce tipping.
It looks like the design takes up a lot of real estate on the deck.
Yes.
What is your feedback from your customer on that?
So far, we have it designed this way to spread out the load. Like we said, we wanted to keep things spread out. But in terms of feedback from the customer, we haven't gotten much feedback for it being so big on the boat.
The boat that this is to be used on isn't designed yet.
All right, and as our next group comes up, I just wanted to say we actually have Engineering 101 students arriving. So I wanted to warn you all that they will be here from around now, and then we'll be visiting you at your tables. So, because they also will be assessing the students today too. All right. We got about 3 more left. Thank you all for being so patient. If you need the bathrooms, there's some around the corner that way. And on to our next one.
Good morning, everyone. We're raising the cage Oyster Innovation. I'm Harmon Preet. This is Bob. That's Karen. That's Anthony. Our customer is Hollywood Oyster and Dr. T. So let's talk about our client, Hollywood Oyster Company, and the struggles they've currently been facing. Hollywood Oyster Company has currently been struggling with manually lifting and dumping oyster bins, which not only leads to injuries, but consumes a lot of manpower and time consumption. Our team's solution is to design a system to lift and dump these oyster bins. In order to do so, we talked to our client and gathered a couple of system requirements, such as lifting and dumping a 400-pound oyster bin, corrosion resistant due to the weather it's going to be in, spatially efficient, and starting low to the ground. Our team design goal is to lift and dump an oyster bin in less than 30 seconds.
Using the key requirement, we were able to initialize the design process. The early design concept involved a movable scissor lift to lift the bins and a set of linkages in order to perform the dumping operation. This was the design we followed for prototype 1. On the right, you can see the first prototype. However, that prototype had some issues. First, the vertical starting position was too high. Then, there were many moving parts, which would lead to frictional losses. And the system also required a large and a heavy base, which would add more material.
After prototype 1, we did an on-site visit to Hollywood Oyster Company where we met with the client. And the client showed us that he had a produce dumper in the storage facility, and he stated that he would like something that's very similar to it. Causing that, we had a few more new system requirements. We increased the dumping height, side loading for pallet jack compatibility on the barge, compatible with multiple bin sizes, and it will be less than 500 pounds. In order to do so, we changed our design direction and reverse engineered the client's produce dumper that they had in the storage facility.
Shown here is the SolidWorks model of our final design. The top video should display the lifting action where two linear actuators act to lift a holder which raises the orange oyster bin. Once the oyster bin is clamped between the holder and the top, two other linear actuators act to push and tilt and rotate the oyster bin until the oysters are dumped into the stationary hopper.
For this project, we were tasked with designing a full-scale model and then building and assembling a scale model as a proof of concept. For our full-scale model, we did research and created a plan for our bill of materials, material selection, as well as an assembly plan, where the testing would be mostly limited to general analysis, high-stress areas, bearing load calculations, where the scale model was more limited towards just the assembly of the proof of concept and time trials. For the fabrication of the full-scale model, we have the materials selected was aluminum 6061 and stainless steel 316. These were picked because they were high applications in marine use, as well as weldability, as well as corrosion resistance. The welding would be tungsten gas arc welding or TIG welding, which is popular in marine use, as well as being able to withstand, and it's applicable in thin to medium-sized thicknesses for aluminum, and the filler material was aluminum 5356 because this mimics the strength stiffness material.
For the full-scale system, we completed power calculations where we found that the lifting actuators would require 0.12 horsepower each, and the tilting actuators would require 0.31 horsepower each. We then sourced actuators online and found the safety factor for the ratio of the accessible power to the necessary power. That would be for the lifting actuators 1.31 and 1.46 for the tilting actuators. We also completed analysis to determine if we could build the system out of aluminum and if it would still withstand the stresses placed upon it. So we completed buckling analysis where we determined that due to the slenderness ratio, the beams of the base would actually be more likely to fail under compression than buckling. So we then completed factor of safety analysis where we compared the yield stress of the aluminum to the applied stress that we plan to place upon the system. We found that we could use aluminum with an interior shell of 2.5 inches, which would result in a factor of safety of 18. We did not further shell the system because we did not want the aluminum to be too thin as to cause issues with welding during fabrication. Additionally, we completed fatigue life analysis to see if the system would withstand many cycles of use. We found through research that there were stress cycle graphs, or SN curves, that showed under 10,000 psi loading, the material, which we found these graphs for aluminum 6061 that is welded and exposed to salt water, those would last for 100,000 cycles, which would translate into roughly 27 years for our customer. Though we don't even plan to place 10,000 psi, we plan to place 500 psi on the system. So we're estimating minimum 30 years use for the Hollywood Oyster Company.
A $200 budget was allocated for the proof of concept scale model. We created the bill of material, which include the main component 3D printed part with 50% infill, 4 linear actuator, and the electronic used in order to control the actuators. Shown here are the main electric components used to control the actuators. We have the Arduino board. The Arduino board has low voltage and low current. That's why we needed a motor driver in order to amplify these signals. And also the motor driver allows to switch the polarity of the power supplies. Hence, we can extend and contract the actuators.
This video would show the scale model doing the time trial, where the lifting would take between 10 to 15 seconds, and the tilting would show between 15 to 20, which is well underneath the 30-second time limit we did. The final assembly and full testing will be completed by May 11th.
This is the timeline for our project since the beginning of the semester. In February, it was mainly about identifying the customer needs, doing some preliminary research. And in March, we went to the farm, the Oyster farm, and we were able to modify our design.
Moving into April, we completed the CAD models for the FEA and the FEA for the high-risk stress areas. In this current month, we have had our 3D parts printed, optimized our full-scale design, and just finalizing our verification and testing reports and our final reports for the project. Thank you.
So Dr. Tobolewski wants to know where you got the 500 PSI stresses from.
The 500 psi stresses were actually generally worst case scenario for each beam because the Oyster bin is roughly 400 pounds, but including the weight of the top of the assembly as well as water and any other mud, we exceeded well over that just to ensure that it's well within the range of acceptable safety factors.
We also, this analysis was completed after we had shelled the aluminum as well. So it accounts for the shelling, and that's when we found the 500 PSI.
So what is the actual max load that, like, of oysters that your client can use with this design?
Well, I guess we have not determined an actual maximum load that would lead to failure, but they estimate that they would only use 400-pound bins when they're completely full. So we actually had designed for 420, but we have been saying 400 because that's what they stated in their customer needs.
All right. Congratulations. Thank you very much. All right, we're down to our last two. You guys are doing great. Whoops. Oops, oops. There we go. All right. There you go. And then and also check YouTube if you want to. There's a lot of nice comments for you all that are being put in YouTube. Maybe your mom or dad. Be told by your parents to hire you.
We are the Oyster Retrieval System, Group 13, God's Hand. I am Jacob, this is Simon, Andrew, and Tom. For our system, we were sponsored by Dr. Tobolewski and the Hollywood Oyster in order to retrieve oyster cages that are sitting at the bottom of a lake. The current system uses a long rope spread from one side of the river to the other, and they wanted to remove this rope because it's currently interfering with certain wildlife, and because of how high up it is, because it's laying on the top surface of the water, it's interfering with passing boats and other traffic. So our goal is to lift 400-pound cages out of the water without affecting any of the surrounding environments or the environment that the oysters are living in. So in order to do this, we also have to re-drop the cages back into the water safely without harming any of the oysters.
Based on the voice of the customer, we came up with several initial concept designs. Initially, we were going to do a balloon, but we realized that that would impact the environment, which is something that the customer did not want. So we moved on to a claw, but we realized that with the time given for this project, it would not be feasible. So we moved on to magnets for the electromagnet in order to find one that was able to lift the cage and be used underwater. It would be way over our budget, so we looked for fishing magnets. With fishing magnets, we realized that there would be slipping, and we didn't really have a good way to remove the magnets. So we ended up using a hybrid design that is both the permanent magnet and the electromagnet. So without altering the boat crane or cage, our general design is to use a 3/16" galvanized steel and a magnet that is able to lift about 600 to 1,000 pounds in order to efficiently lift the cages out of the water. Our design will incorporate a maglock.
So as you can see here, this is our CAD model of the full scale model. So this is a 26-inch diameter galvanized steel plate, and along it there are 4 half-inch eyelet screws, and those are made out of stainless steel. So for the CAD itself, the steel plate was done in-house by us, and the eyelet screws CAD was obtained through McMaster. Oh, sorry. So with regards to the full-scale model, will be done through a outside source. So currently we do not have the full-scale model. We have a scale model, which is outside, and the estimated cost of that scale model was $50. The fabrication for our full-scale model was done to keep in mind to lower the cost of each unit available, as there will be many units created, and the process was done so that it could be easily repeatable, so that machining costs could be lowered as much as possible.
As for testing, we've done magnet strength testing and slip testing. For the magnet strength testing, we placed a bunch of fiber blocks onto a steel plate, and then we used the crane scale and chain in order to find how much force the magnet could lift before failure. The slipping test was done in COMSOL, which will be shown in the later slides.
So with regards to, that was our physical testing. In regards to simulation testing, this is our FEA analysis. So from here, a applied load of 4 times the expected load was done. And as you can see here, the stress concentrations are negligible. And on the next slide, you can see that the deformations on here are also negligible, with the greatest deformation being a 10 to the negative 6 millimeter. Thus, there should be no failures along the plate or along the screws.
So as stated earlier, we need our design to sit below the water to allow boats to pass. But since we're using a plate, it can't sit on top of the cage, or else that will obstruct the oyster growth. To combat this, we decided to add aquatic foam around the perimeter of the plate to float it. On this side, you can see the calculation needed, the volume of water displacement needed to float the plate. And on this slide shows you how much water will be displaced by our perimeter of foam, when we get a factor of safety of roughly 1.1, meaning we can float the plate that's needed.
So for our slip test, we used a online software called COMSOL, and approaching the middle of the plate, and then as we approach the end of the plate, the red line is indicating the forces of the magnet acting on the plate in the Y direction, and the blue line is in the X direction. Our COMSOL approaches the edge of the plate, the Y forces as it leaves the plate drop suddenly, and then as it fully comes off the plate, it leaves almost completely. For our X direction, there is a lot of slip, as you can see. As it approaches the edge of the plate, there is a resistance force that pushes it back onto, but it backs up our philosophy that slip is going to be a big deal in the future.
So here's our budget from the preliminary design phase. We were given a total of 200. We only used 130, so we saved roughly $70. Here's a breakdown parts list for the full design. It is to note that the magnets would be a one-time purchase and would only have to be replaced every couple of years through wear and tear. Everything else would be a one-time charge per cage, and we expect they would last the lifetime of each cage.
For the timeline of our project, we started on February 2nd, and we plan to finish the final design by May 15th. In that time, we created 2 prototypes. The first one was the claw, and the second one was the first magnet prototype, and we generated a lot of concept designs. Any questions?
Okay, so first, just clarifying, is this like a line that's gonna be sent into the water with the magnet and retrieving? And then I have a follow-up question once you answer that.
Oh, okay, so our design pretty much is just the plate is floating above a oyster cage, which is sitting at the bottom of the river, and our project is in tandem with a few of the other oyster cage projects that you saw earlier. So specifically with the crane cage, with the crane group, our design is just a rope that attaches off the end of that crane, and it's just a magnet at the end of that rope, which will be attaching to the plate.
Okay, so with that, with moving currents, and how do you ensure that the magnet is actually going to attach to that and not move and pick up something else that's on the ground or the bottom of the
So the purpose of our flotation and buoyancy is to bring the plate that we're planning on attaching to above the surface or the base of the riverbed, so that hopefully, or there shouldn't be anything that it should attach to, but also so that we also have a clearance rate of, I think, 2 feet, so that the magnet should drop down and within that 2 feet pull up to the surface.
How is the plate itself attached to the oyster cage itself? What is?
So currently, the oyster cages have a rope that are attached to both of the cages. There's a rope that's tied to it, and then that rope is tied onto currently another rope, which is what we had earlier, which is the system that we're trying to remove. We're keeping the ropes that are attached to the cages themselves and utilizing those ropes onto the eyelet screws, which will be attached to the plate.
Awesome. Congratulations on your All right. And we have our final group for the morning. Yeah.
Okay, good morning. My name is Naomi, beside me is Ian, and over there we have Keith, and we are group 15. From the beginning of the semester, we have been working on an inverted pendulum cart for our customer, Dr. Ankit Goel. So a bit of background, Dr. Goel is part of the UMBC MECI department, and he runs the Estimation Control and Learning Lab. For our project, the overall goal is to design a system with a cart and a pendulum attached to that cart that moves linearly over some sort of track. And we were tasked with measuring the cart position and the pendulum angle. So our key system requirements, we have that the system shall have a repeatable method of measuring the position of the cart and the angle of the pendulum. And our angle measurement should be within plus or minus 0.5 degrees, and our position measurement should be within 0.25% of the true position.
So when it comes to the design of our project, it was crucial to choose parts that not only achieve the key system requirements, but also remain relatively affordable. So first up, we have the ultrasonic sensor, and this measures the position of the track of the cart along the track. And it does this by multiplying the speed of sound by the time it takes for the ultrasonic wave to hit the face of the cart. And it's proven to be accurate within a precision level of less than a centimeter to the true position of the cart. We also have the incremental rotary encoder, and basically this calculates the angular data of the pendulum as it swings by converting the rotational motion of the pendulum as it swings to electrical pulses, and these pulses are converted to angular data using the encoder's pulses per revolution value and the total angle per revolution, which is 360 degrees. So on the electrical side, we use the breadboard that allows us for easy prototyping and also reduces the risk of damaging the Arduino. The Arduino allowed us to control our components such as the sensors, the motors, and we also decided to use an Arduino shield, which allows for safe and secure connections without soldering the components. So the motor was a very big part that we had to choose. It was a very important component of our design, and we had to choose a bidirectional motor that allowed us to move the cart in both directions, back and forth. And one of the most important factor that we took into consideration was the torque required. And to calculate this torque, we used the force that the motor will require to not only move the cart but also overcome the friction that the gear might have along the track. We also did use a motor driver, the L298N H-bridge, and this allowed us to not only control the direction in which the motor is spinning, but also the speed at which the motor was spinning. Also, for the structure of our design and the frame, we used aluminum 8020, and this provided us a strong, durable support, but also remaining relatively lightweight. And it was also very easy to assemble and disassemble, which was done using fasteners and angle brackets. Finally, for the linear motion of our design, the linear motion of the cart, we use the rack and pinion mechanism, which basically converts the rotation of the motor shaft into translational motion while also staying accurate and was relatively affordable.
For the initial design evolution, we have the structure layout, and the dimensions are 1 foot height, 1 foot width by 3 foot length as per the customer specifications. And this was cost effective using the longer length extrusions, cutting down to the lengths we needed and the strength and appearance that we would need for the 5-pound cart maximum. For our bearing options, these bearings both fit directly on the extrusion specifically. Option 1 is more of a side mounted, which would not be ideal for our components. So we stuck with bearing 2 on the right, which would allow us to mount the cart on top and works better in compression. For our cart designs, we wanted to optimize the reduced rotation on the bearing. So we condensed all the components on top of the bearing by the final iteration, where the first iteration you can see that the components are mounted very far from the bearing, which increased the friction. For our final design, we implemented the electronics plate for the Arduino breadboard and the H-bridge, and we have the rack brackets to secure the rack to the extrusions and the sensor mount to point the sensor at the cart. This is a motion analysis video. It might play. Well, the gear would spin and the pendulum is affected by gravity, and then you can just see it swinging. For the fabrication, we utilize 3D printing for the accessibility, the affordability, and the fast prototyping it allowed us to do. These are some of the 3D printed parts we designed. For machining parts, we cut down the extrusions, the rack, to the dimensions we needed for the system boundary, and the electrical components that we programmed being the Arduino to work with the encoder, the motor, and the H-bridge. This is a video of how we assembled it. This probably won't play either. So we can show this later if needed.
So for our testing plan, we plan to mount a phone on a tripod to take stable pictures of the entire system with the pendulum at a specific angle, or any angle, then upload those photos to SolidWorks and measure that angle and confirm that our Arduino actually runs and gives us the same angle within our tolerance. For the position of the cart, we plan to use calipers to measure arbitrary distances and again verify that the Arduino gives us the values to our tolerance. And for the Arduino program, we plan to run various cycles of the pendulum and make sure that every piece of data that's collected can be referred back to for any analysis needed. So our budget breakdown, we have 3 major categories: hardware, structure, and electrical, and in total we spent $409.87. And here we have our timeline. We could, because we started the project from the beginning of the semester, you can see we allotted a significant amount of time to each phase of the project, including like early development, purchasing, testing. And we have some time at the end of, like from now towards the end of the semester, to finish up any testing and analysis we need to do on the project. That is all for you. Thank you for attending our presentation. Any questions?
So the ultrasonic sensor must be pretty sensitive, I guess, with the distances, and the pendulum, I guess, has to be like very precise with the timing. What about, have you had any concerns or issues with delay and time delay on the signals passing?
We did not have any delay, especially for the ultrasonic sensor. Our testing revealed that it was very accurate within less than a centimeter, which was acceptable for our key system requirements. For the angular data, we had to perform a little more test. It was a little less responsive than the ultrasonic sensor, so we're currently exploring options to see if there's a better encoder or like better options that we can have to reduce the error that we're experiencing.
Just to clarify the end use case for this, so does the onboard Arduino electronics, does this run the entire control system for the pendulum experiment, or is this outputting to like a computer or to another experiment system, and it's just collecting and passing on that data?
Okay, so it's collecting sensor data from the position and the angular data, but actually from our project goal, we're not supposed to implement a controller. So basically, we just had to make sure that these values are being measured and stored so that later on, future students can implement like a PID controller to actually control the inverter pendulum.
Okay, thank you.
You're welcome.
All right, congratulations. So this concludes the morning session. We do have an afternoon session around 1 o'clock. We're going to allow all my, first off, let's give them a round of applause for amazing job. We're going to now proceed to the hallway where the demos will occur. My one-on-one students, thank you all for showing up. Give the students some time to get themselves together. We'll give you all about 5-ish minutes. Is that okay? And judges, if you need to use the bathroom, get a drink of water, of course. And so everybody, take care. We'll be back around 1 o'clock online. So take care and see you soon.
between 50 and 60?
Yeah.
A few things before we start. In the beginning, I'm going to give a quick introduction. Dr. LaBerge is also going to talk about multidisciplinary, and then immediately we'll have the first group go. Emily, who is out in the hallway, has pink sticky notes to give you your 2-minute warning and your 1-minute warning, and then you're done, okay? There are about 6 judges here, 6 judges here that will be scoring you. And after we're done all the presentations, then you go out there and then they will meet you at your table. They get about a couple minutes of questions, but any other questions they need, they will talk to you out there, okay? There are 2 mics like this. I know there's a lot more of you in multidisciplinary. What I also ask you to do is arrange yourselves so that you're not blocking the screen. We'll have 1 mic here, 1 mic on the other side, hand it to each other as you talk, okay? Also, make sure you're within sort of up to here-ish, because then the camera will actually be able to catch you, okay? Please, put the mic here, not here. Difference, right? We can't hear you if you're like this, and then you're talking, all right? Mic needs to go here. Make sense? Okay, so make sure that's here. And when the last group has finished their presentation part and questions start, I ask the next group to come over here and stand on this side so that we have a seamless transition. Does that make sense for everybody? Presentation stop, questions start, group, go over here, you wait. After they're done, they will leave. We will hand the mics over, and as well as the clicker. This is the clicker. The right arrow advances the slides, the left one reverses it. Simple enough? Excellent. Okay. Any questions for me right now? Yes, Nush. Oh, that's a good question. It does. Somewhere. Oh, you know it. Look at you. Oh, okay, there you go. Okay, who in your group had videos? Or what groups had videos? Can you send 1 rep up here, please? Because I would need to check, because some of them, you didn't give me access, so it's not going to play, or any access. So if you didn't do that, the video is not going to play. So please send 1 rep here. We'll go through them and check them. Make sense? Do that now.
Oh, we have two.
We're just waiting for our judges to show up, you know. They had to get lunch. Now they're all tired. That's right, that's right. Dr. Von Lockett, there's a seat right up here for you. Or right there, too. Either way. And over there. Yeah, you can sit there or there. Do you want to sit whichever you want to sit? Yeah. All right, it is 1 o'clock, and so we're going to go ahead and get started. I assume that we are live wherever my person went to. He would have to tell me. I'm not sure where he went. The light does it. Maybe I know we are on. Are they over there? Are they saying we're alive? I don't know. Because. Are we live? Oh, are we good to start? Yes. Okay, all right. All right, perfect. All right. All right, good afternoon, everybody. Thank you so much. First off, let's give a round of applause to our seniors who came it this far. This is a really tough thing. And I just want to welcome you to the afternoon session of both the mechanical and the multidisciplinary capstone final presentations. These students worked incredibly hard in the last both 15 and 9 months to complete these projects for our clients. We want to thank our clients too for sponsoring these projects. Some of them are online, some of them are here in person, but we do appreciate their to be a part of our community, to be able to help develop these students. This is something we're very excited about. I also want to kind of introduce my colleague, Dr. Von Lockett, who's also Capstone, a part of Capstone now. Say hello. Dr. Von Lockett came to us. Yes, give him a round. He's been an amazing, amazing ally. Also, he's been doing this for how long now? You want to say hello? Say yeah. Since you did in the morning.
Hello, I'm Dr. Von Lockett. I've been here for 8 months or so. This is my second semester at UMBC. I've taught capstone design for 20-something years, and I really like teaching that. I really like teaching it here. Everything that you see that's positive about this course, the multidisciplinary and the ME was made by the people who came before me. I'm just sort of new here, so I give them all the credit.
Thank you very much, Dr. And Dr. Von Lockett also had the same messaging that I also give, which is the fact that you all students, you are the experts, so take a deep breath. This is your time to really demonstrate that expertise. And parents, we do have a few chairs up here if you're interested that is open. If you're, come on down. As the students get up and whatever, you're welcome to steal their chairs. They can stand. But before we begin, I want to turn this over to my colleague, Dr. Chuck LaBerge, who teaches multidisciplinary, and he's going to kind of give you a brief introduction of what exactly happens in that course.
Hi, as Jamie said, I am Chuck LaBerge. I teach computer engineering 450, 451. That's the only fully integrated 2-semester capstone course offered at UMBC in the engineering programs. For about a decade or a little more, we have had a couple of mechanical engineers each year take that course and giving us a little bit of multidisciplinary capability. Last academic year, due to Jamie's fine efforts, Northrop Grumman gave us a grant to develop that program further, and we are now to the point where we have 30 computer engineers.
This is our second year, basically.
This is our second year. We have 30 computer engineers, 20 mechanical engineers-ish, and 6 or 7 computer scientists working in a multidisciplinary way on their individual projects for the entire year. Before I came to UMBC, I worked for Honeywell and its predecessor companies for 3 decades, and I can firmly state this is the way engineering gets done in the non-academic world. It's always multidisciplinary. I never worked on a team that wasn't. Because CompE 450, 451 was a convenient vehicle, that's the test bed we've been using, and we would really like to continue being able to do this. I'm glad that we have 6 multidisciplinary teams here. I have 4 more teams in that course, but they're pretty much computer engineering only. Anyway, I hope you enjoy the presentations. We're confident in our students. Thanks for inviting us.
Thank you. And I do apologize. I failed to introduce myself. I am Dr. Jamie Gerganis. If you are parents or otherwise, you would hear me call Prof G. That seems to be my kind of nickname over here. And so that's what the students generally call us. But this is not about us. We want to celebrate the students. So we're going to go ahead and turn it over to our first. Always the first is always the hard to go. You ready? All right. Come on over, grab a microphone.
Good afternoon, everyone. Thank you so much for coming. My name is Noah Springer.
I'm Peter Serp.
And I'm Billy Knoll.
And we are SkyCal. So we worked with BG&E this semester, specifically their uncrewed aerial systems division. They were looking for a drone payload that they could use to fly around power lines and measure the diameter of the cables in use. The reason for it basically boiled down to capacity planning. Using a drone in this manner would be far safer and more efficient than traditional methods such as sending someone up in a bucket truck. So a couple key requirements that we abided by. Functionally, it had to do its job. It had to measure that diameter of the cable, and more importantly, get that measurement to the drone operator, preferably in live time. On the performance side of things, it needed to weigh less than a pound due to it being a payload. And also, this working range was given to us by a set of wire standards by BG&E. So with our first prototype, we just wanted to make sure that it worked as intended. Focus on that overall functionality. The left-hand picture is a CAD model of our design. The transparent section that you can see is what we're going to refer to as the fixed jaw or the housing of the device. And the fully colored portion is what we refer to as the movable jaw or the linear jaw. The movable jaw slides back and forth on the linear bearings, pushing into the indicator on the side, and it shoots that measurement up to the drone camera. You can kind of see it in the picture, but that fixed jaw has 2 points of contact on the wire, and the movable jaw has 1 point of contact. This helps triangulate that wire in the jaws for a more precise measurement. The entire device was 3D printed, took roughly 20 hours using minimal support material. This was nice for rapid prototyping, and we were fortunate enough to go ahead and test it at BG&E's test facility. So a couple things that we observed, that the functionality was a success. It worked as intended, and the jaw contact actually did show that a wire alignment. But we did see some issues. It was very unstable when sitting on top of the wire, and also we got some concerns from the pilot. Specifically, the depth perception and the alignment, he couldn't really tell if he was actually on the wire. Also, due to a mishap in the print configuration, there were some slight notches on the jaw that led to inaccurate measurements.
So our issues from prototype 1 testing helped us figure out what changes we needed to implement in the design of prototype number 2. First of all, we wanted to improve that stability, so we moved the digital indicator that was initially on the side of the device to the top and center. However, that doesn't improve the center of gravity alone. We also needed to add more weight into the bottom portion of the device. So in that long fixed jaw, we added more weight in the form of lead pellets to properly make the center of gravity better. And then to fix the measurement accuracy, we changed the print configuration to eliminate those notches in the fixed jaw that were there in prototype 1. We designed this prototype to fit the 2-pound weight capacity that was given to us by our customer. The total weight for prototype 2 came out to around 21 ounces. And to help the depth perception issue, we added tabs to the side of the prototype that you can see in this picture on the left. And that helped the drone pilot see whether or not the jaws were fully open over the wire diameter, so we're getting the right measurement. And also to help ease of use, we changed the fixed jaw to a long paddle-like, and it originally mimicked this movable jaw, but that helps the drone pilot catch the device on the wire and repeatedly lower it to get a measurement, so you can get more than one measurement in a flight.
So testing helped us see that the device was more stable, but the weight was too high for the smaller drone. So we need to reduce the weight in the final design, but measurement accuracy and user interface was fixed. And we also wanted to focus on fixing the repetitive and difficult calibration that we had in the second prototype.
For our final design, our biggest concern was still lowering that center of gravity. We accomplished this by optimizing the locations of the mass concentrations, including the digital indicator and the bearings. We would replace the steel ball bearings with nylon glass ball bearings to reduce weight, as well as lengthen the fixed jaw to reduce the amount of weight required for ballast. Measurement accuracy was improved by adding a solid surface to the solid jaw so it contacts the spiral circumference of the wire more evenly. And our final design calibration is very simple. As long as the device is turned on with the jaws closed, it is calibrated and ready for use. All the parts were 3D printed. The two halves were assembled with screws and adhesive. And we created an insert to house those lead pellets that Evelyn mentioned earlier. So now those are all enclosed and inserted in the bottom of the fixed jaw. System requirement verification was done through demonstration, testing, and analysis. Demonstration requirements were completed during test flights at BGE facility. We were able to measure the wire 16 times in a 15-minute flight. Test requirements were done on a calibrated device, such as weighing the device 14 ounces on a calibrated scale. And requirements requiring analysis verification, such as the center of gravity, were completed using computer-aided design software.
So one of the other requirements that we were trying to meet was to have a tolerance of our measurement to be within about 0.02 of an inch. So we machined samples down to really the most used wire sizes that BG&E uses so that we can take those measurements and compare to the standards. So after using a probability density function and taking about 8 tests per wire, we're able to see that we have about 99.9% probability for most of these that the true wire size lands within our tolerance of 0.02. So for our final budget, you can see that we ended up using $176 of our $200 budget. This leaves us with about $23 to spare. So at the end of February, we were able to assemble and test our first prototype. About midway through March, we were able to assemble and test our second prototype. At the end of April, we had our final design printed and tested, and on May 3rd, we were able to have the customer scheduled demonstration. So here you can see pictures of our actual demonstration to BG&E at the BG&E facility. They were very happy with our device and our results, and they actually told us that our device is ready to be used in the field and that they plan on using it. So here's our references, and any questions?
Can you explain how you went with that design that you had from the first prototype and you iterated it? Were there any other design considerations?
So given the task of measuring the diameter of a device, we were basically mimicking other calibrated instruments that measured diameters, the most commonly known as like a caliper, whether it be veneer, dial, or digital. The indicator we used is a common lab and machine shop tool for measuring displacement. So we knew we would use 2 parallel jaws, and then the linear motion, we incorporated the 3D printed design as opposed to a commercial linear bearing. And our 3D printed bearing incorporated with the 22 millimeter bearings gives like a lighter and less friction bearing than like commercially available linear bearings. I hope that answered your question.
So, yeah, when you drop it, it's closed shut, I assume? Like,
yes, the jaw starting position is shut, and that allows us to take multiple measurements per flight.
Okay.
Yep.
Okay. And how's that mechanism? So as you drop it, right, it opens up to measure the diameter, and then you lift it, it closes again.
Yes. The travel indicator has a very light spring inside of it, and that is the only spring that's closing the jaw. Now, once the device lowers on the wire, you want to go to prototype 2 or the final design. You'll notice we incorporated a V shape at the top of where the wire sits. And that V shape on both ends of the body are contacting the wire in 4 places, ensuring that it's perpendicular to the wire, so there's no load being pushed against that movable spring-loaded jaw. It's just there to take an accurate measurement.
How did you come to a stiffness, spring stiffness that would work for what you're trying to achieve?
Sure. Yeah. So it goes back to what Billy was saying. We were torn between whether we wanted the jaws to start open or closed. Starting open, we have to have some type of locking mechanism for it to then be released to close. To take repetitive measurements, we thought it'd be easier if they start closed and then open. We just used the force of the spring, the dial indicator, because it was sufficient, and it actually pushed the linear bearing to start closed without any force. And it was a part of our first prototype to see whether the weight of the prototype would actually create enough force to push the linear spring and open up the jaws, and it proved to be a success, so we just ran with it.
Yeah, that's a really great question. To piggyback on that, we knew we wanted the lightest spring possible to minimize the weight of the payload. So that was really, that first prototype was like a really quick idea to see if just that light spring from the indicator would give us a precision measurement.
All right, more questions, of course, will come at your demo. Congratulations. Thank you very much. Give a round of applause. Can you give them the microphone?
Oh, thanks. B and I should be on the same side because we alternate, like we're stateside.
All right, and you got the clicker? All right, and here you go. Just so you know, there's lots of comments coming in on the chat, so that's for YouTube, and whenever you all are ready.
All right, good afternoon. This is Team 6. My name is Charles Benici.
I'm Manessa Jang Mahader.
I'm Eddie Presno.
I'm Pete Van.
And we are working on the coaxial counter-rotating vertical axis wind turbine. So for some background, our customer is Dr. Malin Yu of the Mechanical Engineering Department. He has tasked us with a number of goals listed here, the main one being constructing a vertical axis wind turbine that counter-rotates in order to generate electricity. Some system requirements here. Each turbine set must be able to produce electricity on its own when subjected to the given wind speed as a target, and the turbine should exhibit some sort of torque disconnect, whether it be a clutch or one-way bearings, in case of a malfunction. Some more of the requirements are listed here, and the most important ones for a wind turbine is the geometry, and these geometries were provided by Dr. Malin Yu, so we had no say in the design of them. For the first evolution of the design, we knew that we had to incorporate the counter rotation as the most important part, so we decided to use a bevel gearbox, as it is a quick and simple way to take 2 opposite direction loads and send it into one single output. And later work was focusing on incorporating the torque disconnect.
So once we had agreed on the bevel gear configuration after our first few meetings with our client, we made our initial CAD model using files provided by the sponsors, using that blade geometry defined by Dr. Yu's research. Then subsequently we expanded upon that to include a support structure and also the gear train components, as well as the locking bearing assemblies. And once we had this model, it allowed us to determine all the component dimensions, which made assembly go a lot smoother. And here we have an animation of our initial concept, just to verify that it is able to counter-rotate in the manner that we want it to. And then on the next slide, so as far as analysis, the first step was kind of working out the weight of everything and making sure that the materials that we had chosen would be able to withstand the forces they were subject to. The turbine mass was quite low, and also using the counter-rotation device minimizes forces on the base. And then using calculations from Dr. Yu's research, we found that the torque produced by the turbines was relatively low, which proved that we were able to use the bearings that we had sourced. And here's an FEA that we conducted on our CAD model. Shown here are the two highest stress areas. Even though those are the two highest stress areas, they're both well within what the materials can handle. On the left side, we have the wooden support rods for the turbines. Those are at 15% of their yield strength. And then on the right side there are the aluminum supports, which are also well within their strength.
In terms of fabrication, we decided to 3D print a variety of components. So our Savonius blades up here, our Darius here, and here's the top view of the Darius, so you can see that airfoil shape. We also 3D printed a bore adapter, which is that bottom left image, our Darius support hubs, and our upper and lower clutch housings. We also decided, on the following slide, we also decided to manufacture a couple parts by buying large axles and cutting them down to the length that we wanted. So the top image shows the aluminum rods that we use for the base and the gearbox housing supports. We have our wooden dowels that we use for the Darius connecting rods. And we also had steel shafts here that we use to support the top and bottom turbines, the plywood for the gearbox housing, and also 2x4s for the base. In terms of woodworking and machining, so for our 2x4s, we cut out the center portions of them with the saw and we lap jointed them together. For our gearbox housing, the top and bottom have two square slabs of plywood, and then they have a round center hole going through them. For our 2x4s, we also use a drill press to cut 1/2-inch diameter bores for our aluminum rods to be press fit into the base and support it. Also continuing with woodworking and machining, our middle gearbox housing was supported using nuts and bolts. We create a slot here and here to prevent the gearbox from moving like this. We also elevated the gearbox to reduce the vertical friction on the bottom turbine. So this is an overview of our budget. This is all the main components of our prototype. So we spent $194 out of our flexible $200 budget. Not shown here is any 3D printing filament, any fasteners, or any tools or equipment that were used, because those were provided either by our sponsor, our personal tools, or by UMBC facilities.
So for testing, we want to closely follow our system requirements. First, we want to test for the modularity of the design by removing the top turbine, and that way the bottom turbine should be able to rotate the bevel gearbox by itself. As for a wind supply, temporarily, we use a box fan that is placed in front of the turbine that produces wind flowing at around 4 meters per second. Eventually, we'll be testing at a much larger wind wall at about 25 fans. Next slide. So secondly, we want to test for the counter-rotation mechanism and the independence between the top and bottom turbine. On the left figure, this is the correct operation. As you can see, the green pairs of arrows indicate that the main shaft and the bevel gear shaft are engaged with one another through the one-way clutch, and they're both rotating to translate torque to the horizontal shaft. And for the middle and the right figures, we will purposely slow down the top turbine and turn it in the wrong direction, respectively. In both instances, it should disengage the main shaft from the bevel gear shaft. Meanwhile, the bottom shaft should still be engaged and spin as normal and not affected. This test aims to imitate fluid-like condition where the wind supply is not always constant, and in the event that one slows down, it will not slow down the one that has air supply, which will happen if they were to be coupled together without the one-way clutch. So from the preliminary testing, we found some results that give us good insights on what to improve next. First of all, the overall structure is fairly stable. The system does function with a single turbine. However, the bevel gearbox actually introduced a lot of static friction. As for the current design, the dual turbine setup does not start automatically. However, it does demonstrate the counter-rotation mechanism and the one-way clutch. So the rotational friction is apparent in the thrust bearing that we chose, possibly preventing the turbine from self-starting. The team is investigating some new implementation to help reduce static friction and increase stability. Finally, this is a general timeline that we've laid out for the project from the beginning. We've been following every single step consistently. Right now, we're at the testing assessing phase, and we have about 5 days to a week to improve our design. before the final phase, which is evaluation and demonstration to Prof G on May 15. And that concludes our presentation.
Do you know how much friction is required to get, how much friction is in the bevel gears? So how much friction, static friction you need to overcome? So those turbines need to overcome in order to get it going?
We haven't done any calculation. Well, the bevel gear was ordered on Amazon, and when we got it, it felt really easy to turn by hand, so it felt like there was no friction. However, when we insert that into the one-way clutch, there's a little bit of play between the shaft itself and the one-way clutch, even though they were both on paper the same dimension. So when there's a little bit of a tilt, there will be a different contact point. There's a lot of static friction that way. And just by itself, when you add the gearbox on top, it just, the way that the bevel gear meshes one another, there's a lot of static friction that way in contrast to if they were to be on the same axis of meshing, if that makes sense.
All right, thank you very much. Good job. Congratulations. Thank you. And then the next team want to come on up. I just wanted to also mention that our judges are consistent of American Society of Mechanical Engineers that are a professional society. If we would give them a round of applause for taking the time of their schedules for being here today.
Good afternoon, everyone. My name is Ian Jacobs.
My name is Caitlin Ruddick.
I'm Christopher Biscatch.
And I'm William Bassett.
We are WIC Industries, and today we'll be discussing our wind turbine project with you. Start with some background information. We had two sponsors for our project, Dr. Eggleton and Dr. Bhattacharya. They worked with us over the semester and helped guide us through the design process. The project beneficiaries will be the students over at Shady Grove. Once everything's done, at the end of the semester, we will transport our system over to Shady Grove, and they'll be using it in their fluids lab. To start off with our project requirements, or excuse me, our project goals, we were tasked with installing and characterizing a horizontal axis wind turbine system. So basically, we were given a pre-purchased turbine, and our job was to create some sort of a base for it, and then introduce a wind delivery system, bring them together, and create like a full lab setup. So initially, we started off by laying out some requirements for our two main components of the system. First, for the wind turbine base, we wanted to support at least 100 pounds. We wanted to minimize the deflection to less than 1/4 of an inch. We wanted it to be adjustable and easily maneuverable so you can move it around within a lab setting. For the wind delivery system, we had to produce at least a wind speed of 7 miles per hour for the wind turbine to work appropriately. And then the output air of our fan or wind delivery system had to cover at least 80% of the cross-sectional area of the turbine blades.
Throughout the design process for the wind turbine base, we wanted to prioritize the yield strength as well as the cost. Again, with the system requirements, we wanted to prioritize maneuverability as well as the reduced deflection. And with that, on the right side, we can see our final design. For that, we wanted to make sure we could fit all the components as well as the wind turbine itself. And the additional support towards the center was to reduce that deflection.
In designing the base of the cart, we completed many different force and moment calculations. We used Bett's limit to determine the thrust force created on the turbine, and then used that thrust force to find the moment created on the cart. We also calculated the reaction forces for each of the different sets of wheels on the base and used these forces and moments to create a force moment diagram. And we found that the maximum moment was about 34.85 foot-pounds.
Throughout the design process for the wind delivery system, there were a couple options that we considered for that. The first of which was to utilize the exhaust from the wind tunnel at USG. Unfortunately, with that, we were not able to use that option after analyzing with mass conservation. So we looked at the second option, which was to utilize fans. And we found that an industrial fan was the most appropriate option for that because it met the surface area as well as the variable speeds outlined in our system requirements. And with that also, we needed to incorporate a honeycomb structure to that design to ensure a uniform airflow to the wind turbine.
Manufacturing these components required the use of power tools. The steel plate, for example, needed holes drilled into it to mount the caster wheels as well as the rotator system. A wooden base was also built for the wind delivery system, and further plans this semester is we still need to build the frame for the honeycomb structure. Now, once we had it all built, we had to test it before we brought it over to Shady Grove. A strong 155-pound weight was placed on the plate to check for deflection, and further we used the anemometer to confirm the wind speeds purchased from that fan are exactly what was advertised. So then we took it over to Shady Grove, we loaded up the wind turbine and got it all set up, and we successfully ran a test. The power created was as expected. However, one caveat, this here is the testing panel, the display panel for the wind turbine. You can see the velocity into turbine and velocity after turbine showed a static value of 1. We're still not sure why that's not working. We believe it's a sensor issue. We have since reached out to the manufacturers to find a solution to that problem. Now here we have two short clips here for you. It's showing the wind turbine in action. We see the big yellow industrial fan, and then you can see Ian reading off the displays and recording data.
After completing testing, we were able to compare experimental results to the data provided from the manufacturer. During testing, we ran 3 different distances between the fan and the turbine, and then at each distance, we also tested 3 different velocities. We were able to conclude that our experimental data correctly correlated with the manufacturer's results. And then with our data, we were also able to produce 2 different plots. We were able to compare the airspeed to the RPM and found that as airspeed increased, the RPM of the turbine also increased. And then comparing the air velocity to the power output of the turbine, we found that at each distance, the power of the turbine also increased with velocity.
Here we have outlined our budget as well as our spending for the project. We were allotted $200 by UMBC and an additional $1,000 to $2,000 from USG. With that, we spent approximately $1,000 over the course of this project. We are still under budget with about $200 to $1,200 remaining. Here is a summary of our timeline throughout the course of the project. Currently, we're in the implementation phase, validation, verification, testing. Also, with that, next week we'll be, again, planning on incorporating the honeycomb structure into the testing of the system to ensure that that system requirement for uniform airflow is met. And again, our experience throughout the course of this project, we were successfully able to implement and execute the design requirements for the project and be able to support the operation of the horizontal axis wind turbine. And then with that, we were able to do the collection of data for that and ensure that it was meeting the requirements outlined by the manufacturer. Again, throughout the course of this project, we were able to apply a lot of the fundamentals that we've learned here at UMBC and enhance our communication and technical skills. Here's our references. Any questions?
Questions from our judges?
Great presentation. I had a question on the nonlinearity of the turbine data that you guys received. I was wondering what, if you guys could go back to this slide. Yeah, that one. What factors in the design of the experiment might have led to some of that deviation from a linear trend?
So currently, because we're having issues with the velocity output of the sensors, we use the anemometer to get the velocity measurements, and we're not 100% sure that all the readings are like super close, but they should be around the right values, but there's still some uncertainty with those results. So next week, we're hoping on completing final testing to get some more linear results.
Again, to caveat off that as well, like Bill mentioned, some of the sensors on the wind turbine aren't functioning, so that's kind of limiting our data as well. So,
thank you.
Yeah. All right. Very good. Congratulations. Wow. Thank you. And you guys. But you guys, I know who you are.
Good afternoon, everyone. We are rolling with Caleb. Our client is VME, or Volunteers for Medical Engineering. My name is Allie Hunter, and to my left we have Connor Wingate, Brittany Castle, and Nadeem Nasser. Our client, Caleb, is 15 years old, and he has cerebral palsy. His powered wheelchair works well day to day, but poses challenges when it comes to travel. The family often travels across state lines, so it would be convenient for them to travel by plane, but due to the powered wheelchair being so big and also has the battery, it would have to be stored in cargo, and the family is justifiably concerned that it would be damaged or lost when it's stored in cargo. Additionally, even for small trips like running errands, Caleb's mom has to lift the wheelchair in and out of the truck by herself, and the wheelchair is just too heavy for one person to lift alone. So our goal is to provide a lightweight travel wheelchair for the family to travel with ease. In order for the chair to be considered lightweight, it must be under 50 pounds. It also must be stored on the cabin of the airplane and fit inside the storage compartment designated for wheelchairs. All of the removable components must be able to fit inside a bag that can be stored underneath the plane seat. The process must be simple enough for the combined assembly and disassembly time to be under 5 minutes, and an instruction manual will be provided for the family with a clear step-by-step guide of the assembly process that will also be useful in case a flight attendant is the one doing the assembly process. Comfort is also a top priority for Caleb, so all of the supports that he needs, including the lateral, head, leg, and arm supports, will be included with the wheelchair.
Our original idea for the design was going to be a transport chair that Caleb's caretaker would operate that would be stored in the overhead compartment of an aircraft with all entirely custom supports. However, we found that Caleb's family uses Southwest, which has a wheelchair-specific compartment, which allows us to give him a self-propelled wheelchair that he himself will be able to roll. We also found that having adjustable and pre-made supports would be more feasible as opposed to the custom ones. We did make some smaller adjustments, such as reinforcing the anti-tilt wheels, as those that we have found that those with similar wheelchairs have had experiences where their anti-tilt wheels are not as durable, so we reinforced them. We also decided to include things such as a cell phone holder with a special grip for Caleb, a storage case, and an instructional manual for his convenience. And last but not least, we ourselves tested the original lateral supports and found that they moved a little bit too much, so we reinforced them as well so that they will be able to move less as well as undergo more cycles. So our final design is a So Light wheelchair. It is collapsible and it has been outfitted with a headrest, lateral supports, the cell phone holder with grips, and all of the attachments will be able to fit into the suitcase that we have provided, which also will include and fit the leg supports.
So in order to verify that we met all of our requirements for the project, we first began with testing the headrest to make sure we were meeting Caleb's comfort needs. By doing this, we did a FEA analysis on SolidWorks to check the maximum displacement. To do this, we focused on the area where the headrest attaches to the wheelchair itself. We found that our maximum displacement would be approximately 52 micrometers when 10 newtons of force was applied to the headrest, and this was a factor of safety of 3 compared to what we thought Caleb would actually be applying to the headrest. The next thing we needed to test was the final weight of the wheelchair. So we found that the actual weight with the attachments was 33.2 pounds, and without the attachments, it was 26.2 pounds. It would most likely be lifted in the state without the attachments, but either way, this would meet our requirement. We also had to check our size requirements, and we found that when it's folded, which is the state it will be placed into the wheelchair cabin in, that it was 12.6 by 28 by 23 inches, and the carrying case itself for the attachments was 8 by 13 by 16.6 inches. The next thing we wanted to do was verify that our time requirement for assembly and disassembly was met. So we had 10 different people test out assembling and disassembling the wheelchair while provided with the instruction manual we put together. And we just timed them by each aspect there was to assembling and disassembling the chair. Next one. From these tests, we found out that the average assembly time was 1 minute and 49 seconds with a typical standard deviation of 42 seconds. Next one. And we repeated this test as well for disassembly. Not going to spend too long on that. The average disassembly time for this was 1 minute and 42 seconds and a standard deviation of 41.4 seconds. We found from this that even at our maximum standard deviations and our average times, that we were under our 5 minutes total for assembly and disassembly of the wheelchair.
All right, moving to the budget. So we were allocated a total of $950 for the budget. $750 of which came from VME, and UMBC contributed to $200. Our most major expense for this project was the wheelchair itself, where it was our most significant investment, coming at $550, and the headrest at $120. Other items, necessary items are listed on the slide, such as the Velcro material and other storage solutions. Thanks to careful management and for donated items, we managed to have a total budget of $820, having a remaining budget of $128, which leaves us well under budget. For our timeline, we initiated the project back in February, where we started doing backend research and the initial meeting with VME to establish some requirements. In March, we faced a major scope change where we received a new client, Caleb, where we had to adjust our requirements to meet specific needs. That led us to finalize our wheelchair design along with the attachment to ensure the safety and the compliance of storage requirement. April was a busy month where we ordered all the parts, assembled the initial design, and tested the chair with Caleb to ensure its final weight and the functionality of the chair. As of May, we completed the time analysis to make sure that the adjustments and the wheelchair itself is perfect for the user experience, as our goal for this project was not only to make the chair functional, but to make it as user-friendly as possible. We are currently in our final stages of documentation, and we hope to deliver the chair to Caleb next week. That's it. And yeah, I would like to open up any questions you might have.
Can you go back to the slide?
Something with that? Yeah, here. Yes, okay, here. We'll there you go.
Can you go back to the slide of the showing the final wheelchair?
Testing.
Okay, can you go over what parts came with the wheelchair as ordered, and then what were the changes or improvements you made?
There you go.
Sure. So. So the wheelchair itself naturally came with the leg supports as well as the anti-tip, and of course the cushion that's on it as well, not the blue one, but the red and black one. The things that we've added are the head support, that blue belt with the cushions, the lateral support, the phone case, as well as that suitcase that everything goes into. We also added those 2 grip balls that are for his, so that he can operate the phone case.
A lot of the project went into really ensuring through our research that we had a wheelchair that would meet his needs. Even the little things like, can his feet touch the ground when he sits on it, because he kind of likes to walk on it like that. And this helped us, since we had the shorter timeline with the client change, really to make sure that we have enough time to get all those supports we wanted.
Any questions? All right, great job. Thank you very much. Thank you. All right, now we're going to move on to our multidisciplinary group. This is our first time. You guys are the inaugural of coming up here. And you guys. Microphone situation.
Let's just hand it over there and I'll click.
There you go.
Good afternoon, everybody. This is Ava's swing team, and this is our presentation.
This is an overview of our team. One of our team members wasn't able to make it today. I'm Alec Kalish. This is Yoel Fortaleza. This is Jess Turner. That's Daryl Suber, and that's Liz Miller-Knoll.
So again, my name is Jess, and I'm going to go over basically the background. So in the picture in the middle, you can see our client, Ava. Our sponsor is the same as the last team, Volunteer Medical Engineers. Our task is to build a motorized swing for Ava so that her parents don't have to constantly push her when she wants to play outside. Similar to most of these projects, we have a budget from our sponsor, we have a budget from the UMBC combined that we'll be spending. We want to make sure that the control panel we make is operable by the parents, and we want to make sure that Ava is able to swing safely in this swing.
So just to give you some details about our design, you can break our component into 4 components. We have our A-frame and our ADA compliant seat, which will experience the swing motion while the system is in operation. Next, we have a gear system that is directly applying force to the swing seat and will produce the swing motion. Next, we have a bipolar stepper motor, which will drive the gear system and respond to signals being set from a controller system. And lastly, we have a controller system, which is comprised of an accelerometer sensor and 2 Arduinos working in primary and secondary to have motor function logic, read user inputs, and respond to sensor feedback. And we'll also use an LCD display for our timer interface and keyboard switches for our user inputs, specifically for presetting increments and decrementing time and starting and stopping the timer. And all of our electronics are powered by a central power supply.
So for our overall design, we have a steel frame that was free and it met all our safety requirements. The swing mechanism is gears. We're going to add, you don't see in the picture, we're adding a stiffer boards to the back of the seat that'll attach to the frame. And there will be, for a cool factor, remote control color changing lights for Ava to turn on and off. So this is beginning of our design process. We didn't have very many constraints. It needed to fit in an 8 by 6 foot area and support a dynamic weight of over 150 pounds and be set with a timer. For the motor, we determined that we needed a final speed of about half a second. And so using the gear reduction as well as the programming, we're going to try and meet that need of the decreased speed from the motor.
So again, my name is Daryl Suber. We've gone through a few different iterations of the designs, the first being a compound gear train that just involved 3 sets of gears. The second was a compound gear train as well as one-way bearings that wouldn't work because it wouldn't allow for the proper rotation that we were hoping for. And the third was a cam system. Our final design, if you could go to the next slide, is a mixture of using both gears and sprockets. We're going to have 2 gears, one that directly connects to the motor, and then that gear will transfer to a rod just below it. On that rod, we'll also have a freewheel bike sprocket that rotates with torque in one direction and freewheel in the other direction. And that will then mesh with another sprocket on a lower rod that will be connected directly to the seat. Here are some of our original structural design concerns. We wanted to protect the motor and gears by having some type of housing for them. and we wanted to stabilize them onto the frame to make sure that they don't fall off or get damaged in any way. And we also wanted to be able to stabilize the swing onto the concrete at the client's house.
So here are the requirements that we had to meet. As you can see, there are about 6 categories of them, and we split it up by which team is covering them. We have computational requirements, including powering all of our hardware systems, making sure that the components interface with each other, and then we have mechanical requirements at the bottom that basically say the structure is safe and sound and moves as we expect it to. This is basically how we're testing them. A lot of our hardware components were able to be tested just by powering them on and seeing what happens. Then we move up a level by testing hardware systems altogether. We have our controller and the sensor that we connect to each other and make sure they're communicating. And we have the overall swing system, which we will attach our controller and motor to test.
So just to cover a little bit of the electronic requirements that the computer engineering students were tasked with. Essentially, the power system and the controller system are fully housed in 3D printed housing that is sufficiently protected from weather, as well as having proper venting for any kind of temperature control, dealing with any kind of heat as well as water damage that could occur due to this being outside. The 3D prints are primarily in PETG because they are slightly more shockproof and waterproof than PLA, as well as being in multiple pieces for easier assembly in case of any kind of breaks or anything. All the CAD models will be provided to the customers. That way, in case something does break, it can be replaced very easily with commercially available printers and filament. Additionally, we have the computational requirements. This is mostly software as well as integrated systems, essentially. Mostly the 2 Arduinos, the accelerometer, and the control display, as well as the buttons, which are all wired together and directly support the control of the system.
So we didn't have any background information on the frame, so this is a test to see how it might react to the swing in motion. And then in the next slide, we wanted to see how it would handle the different weights.
To wrap up, we have our timeline. You could see a lot of pictures of what we've already done in the tests that we've run. We've made the housing for the power supply to protect it from the weather similar for our control that the parents will be operating. The last steps are basically just to assemble and test. Questions?
Right now, do you have any questions? Well, for now, we're just doing the Ice Meet Judges. Yeah, so if you have questions, we'll be doing our demos after this, and then definitely have more questions. You all good? Oh, you just blew them away. You have no questions. And who's mechanical in here? And who's compy and comp sci? Very good. Thank you very much. Congratulations, guys. Thank you. Yeah, you guys have a lot. Share. All right. So, yes. So, do you guys want Google Slides or
the file.
that one.
There you go. Check 1 2. Check 1 2.
Oh, wait, here's your slide.
Right, this next. Okay.
Hello, my name is Mickey, and I am the leader of this team. And for the past year, we have been developing the automatic multi-site intracerebral therapeutic delivery system. But at the Capstone lab, we are known as the precision injection team. To introduce the team, Ben is our mechanical engineer, Andrew is our computer scientist, and Joe, Jackson, Tyler, and I are computer engineers. So our client and our sponsor is the Program for Image-Guided Neurointerventions at the University of Maryland School of Medicine. And a lot of their research involves executing intracerebral injections on mice, which is a relatively non-trivial procedure as it involves keeping track of several variables such as the animal's vitals, detecting an injection site that avoids surface blood vessels, and then accurately navigating to that injection site and injecting. And then when we wish to expand this to multiple injections, this exponentially increases the difficulty, making the procedure nearly impossible. So that's where we come in. They're looking for an automatic method of executing these multiple intracerebral injections. So for example, taking this image of a mouse brain, we are giving multiple injection locations. We provide a precise injection site for each of those locations, and then we automatically inject. So we have broken down our system into two subsystems to complete our requirements. The first is the Automatic Injection Maneuverability System, or AIMS, and this system is concerned with controlling a M010 injector provided by UMB. And at this stage, we are only concerned with controlling it in the XYZ direction for insertion, and in the future, there will be implementation to control the dial for automatically administering the therapeutic. The second part of the device is the injection site candidacy system. This takes an image of the sample area, identifies blood vessels, and then given multiple injections, provides precise injection coordinates for AIMS to automatically navigate to. Oh, there we go.
For our key requirements, we have a minimum bed size of 25 by 50 by 35 millimeters cubed so that we can accommodate for future brain sizes. We also need to automatically detect an injection site and then navigate to that injection site within a maximum of 100 micrometers and optimally within 10 micrometers. Additionally, we want to be able to take high resolution images.
So this is the progression of our mechanical design. On the left is a picture of the first low fidelity prototype, which we created in fall of last year. And on the right, you can see a CAD model as well as the assembled final device, which we'll be delivering to the customer soon, which was developed over this past semester. So the final device uses a bed slinger design with a fixed x-axis. So the y-axis moves the bed, and then the z-axis, which is the up and down, is attached to the x-axis. The whole thing is held together with a frame made of aluminum extrusions, and everything's attached with brackets made from carbon fiber reinforced PLA, which helps us keep everything as rigid as possible. We've also got high precision lead screws and linear bearings on each axis in order to help keep with the precision as well. And the whole thing is powered by 3 closed loop stepper motors, one for each axis, which have rotary position feedback control, which helps make sure that we're hitting our accuracy targets and improves the precision as well.
So going over some of the design changes to our stepper motor interface, this was what we had in the fall. This is just a simple A4988 driver connected directly to a stepper motor. And while this does work, it is largely inefficient due to the fact that the pins that we use to drive the steps and direction were over file I/O writes. So for each step to move, we had to write effectively to a file, close it, and then continue that. So for a large number of steps, this had a lot of memory complications with our software. So we have decided to move over to a Big Tree Tech Octopus Pro board. This is a board that is used primarily for 3D printers. It's a CNC board that uses G-code. G-code allows us to, over a single G-code command, move the X, Y, and Z axes. So this is way more efficient than our previous design. It also consists of customizable open source firmware. So this allows us to write the maximum bed limits that Tyler briefly mentioned previously, and then as well as the steps per unit distance. And then it also handles all of our operations under the hood. So while we were previously had to manually check for our maximum limits, this will control all of that for us. And then briefly going over our software and hardware implementations. So pictured on the top right here, this is our small form factor computer. This is a Jetson Nano. It has an integrated GPU that helps with our ISCS software. This computer integrates all of our GUI, AIMS, and ISCF software into one machine. This interfaces with the BTT Octopus Pro over a serial connection via USB and issues commands to the BTT Octopus Pro, which then drives the stepper motors using its integrated steppers.
Since our previous motors had various issues such as overheating, we ended up upgrading the size of our motors to NEMA 11, which also allowed us to properly drive the injection apparatus. They also come with integrated rotary encoders, which check how far that they have actually turned so that we can verify that we're moving the correct amount of steps. They have a microstep resolution of 1,000 steps per rotation, so this allows us to calculate the minimum precision that we have on the next slide, which is 1.5 micrometers per step, since we also have a 1.5 millimeter pitch on our lead screws.
Yeah, so to quickly go over the injection site acquisition portion of our project, we have an onboard mini camera to take pictures of the 3mm cranial window. As you can kind of see up here, you'll see better on the next slide of this image. We use a variety of computer vision techniques to take that image on the left and identify the blood vessels here on the right. And those white lines are the blood vessels that the injection site acquisition thing detects. And as you can see on the next slide, the gray dot there is actually the needle, like where we would actually be executing that injection.
I will be going over our preliminary results. As can be seen on the left-hand side, we have our current GUI, which is allowing the user to select specific sites, click the generate button, and the specific sites are sent over to Andrew's machine learning algorithm, which allows us to be returned the correct specific injection sites. And on the right-hand side, we are going through doing a specific demonstration of the actual injection apparatus going through each individual well. This is our current test plan. So we have 2 tests scheduled. We plan on injecting within the center of a well plate. This will be testing the maximum range. And test 2 is going to be injecting within a crosshair pattern, which will be testing for specific precision within each axis. This is our current development schedule, split up into 2 different semesters. Semester 1, we had our low fidelity design, as you can see, and semester 2, we have our current design, and we are planning on doing our final demo and delivery soon. Our current budget, we had an overall budget of $3,000. Our total spent was $2,669.82. Our final device cost was $1,898.
Thank you.
Thank you. Any questions?
Can you explain why you went with in terms of moving the injection needle in the 3 positions, why you built this current design that you have versus just using an arm, maybe a commercially available arm, and then starting with that? Could you just explain?
Yeah, so the main reason we didn't start with a commercially available arm is because of the rigidity. A lot of the times when they're close to the arm, they're pretty solid, but as they extend further out, they can get kind of wobbly. And you know, when you're dealing with injecting into mouse brains, the precision we're aiming for is quite small. So we really wanted to make sure that everything was staying as rigid as possible, exactly where it was supposed to be. The other main reason is just cost. Big robot arms are expensive if you want to get good ones. So. So the requirement for tolerance is to be within 100 microns. We do believe we will hit that. We haven't yet performed the final test so that we have an actual number, but it's somewhere between 10 microns and 100.
Very good. Congratulations. All right, are you PowerPoint or Google Slides? Which, your one? Which one? This one, right? No, what? Yeah. Who's doing?
Next slide.
Okay, hello everybody. My name is Mohammed Nasser, mechanical engineering senior. I will be presenting our project, the vertical axis wind turbine, for our sponsors, Blue Green Energy Solutions, as well as Dr. Yu's research group. I'm joined with
Katab Salih, mechanical engineering.
Austin Collins, mechanical engineering.
Edward Nottingham, computer engineering.
Ryan Murray, computer engineering.
And Kojo Benefo, mechanical engineering.
Now, our project we're tasked with assembling a pre-designed 300-watt vertical axis wind turbine integrated with a pitch control as well as communication system. This project not only serves as our capstone, but it also serves as a proof of concept for future devices of Dr. Yu's research group. So by its nomenclature, this device is a turbine with a vertical axis of rotation, which coupled with its blade pitch control gives it advantage over its horizontal traditional counterpart. For example, it requires lower wind speed and it has omnidirectional wind capturing. This compact design, again, with its scalability, allows it to be ideal in urban environments as well as offshore environments. In addition, it has lower cost and maintenance than its horizontal counterpart.
Good afternoon, everyone. Once again, my name is Austin Collins, Mechanical Engineering, and I'll be reviewing our system design requirements. So our first couple of design requirements are user requested, meaning they come straight from our client. So there are a couple of variables we want our system to record. Those would be angular velocity, wind speed, wind direction, as well as power output. The wind speed and wind direction are collected with an anemometer sensor, and the angular velocity is recorded with a rotary encoder that records the precise rotational position of the turbine. Next, this recorded data will be sent to a designated location for monitoring. The next requirement is that the system shall be able to apply a brake to stop the turbine in the event that that is necessary. And then the next two requirements outline the turbine's ability to adjust the pitch of the blades as well as the electrical load of the turbine based on the conditions that it is in. In higher wind speeds, the electrical load will be increased to provide more power output, and in lower wind speeds, it will be decreased so that the turbine can still operate. And finally, the turbine shall be able to spin from wind speeds of at least 4 meters per second, which is approximately 9 miles per hour. Good afternoon again, I'm Ryan Murray and I'm going to take us through the pitch control system overview. So starting with our two sensors, we have our rotary encoder, which captures turbine speed and position. We also have our anemometer for wind speed and direction. That data is then passed into our Raspberry Pi, which will calculate the ideal angle of attack for each individual turbine blade. That specified angle is then sent to our servo controller, which will adjust each servo to that specific angle.
Hello, once again, my name is Kitab Salih, and I'll be walking you guys through the assembly and the mechanical system of our turbine. First off, we have the chassis, which is consisted of the cast carbon steel tripod base, a bottom shelf that carries the generator, the drive shaft, and the control system. And then next we have the top plate, which carries the pitch control system as well as the Darius blades. Now we have the top half of the turbine, which carries the aluminum tri-blade Darius system, servo pins that are connected to the center shaft, which is around 7 feet in length, as well as a rotating bearing. Next, we have our mechanical systems, which are the trailer brake system, the servo system, and the load generator. So our mechanical system is fairly simple. You know, the wind blows against the blades, it spins the turbine. Everything on the turbine spins except for the top plate, the bottom shelf, and the tripod base. So once the turbine spins, power and electricity goes down to the battery, which then powers the rest of the turbine.
Hello, my name is Coach Benefo, and I'll be talking to you about the braking system. So for the braking system, it sits upon the bottom shelf, which was aforementioned by Kitab, which is the white shelf towards the bottom in the video. And for the braking system, we use the trailer brake, which is a solid gray iron 10-inch brake drum with a 5-lug on 5-inch bolt pattern. And it can withstand a brake load of 3,500 pounds. And it uses electromagnetic brake drums to create attrition and slow the shaft down. In the video, we're manually spinning the system because we were unable to get outside, so we can have wind push on the blades and turn the center shaft. So in the video, Austin and Kitab are turning the center shaft, so then we can then apply a brake through a controller, which is a pressure gauge, on a system from ranging from 1 to 99. 99 being the most amount of brake load you can apply, and 1 being the least. So when we press on the brake, it will come to a complete halt because we used the number we used was 99, which is the greatest amount of braking load we could use.
Good afternoon again. My name is Edward Nottingham. I'm here to talk about the pitch control structure. So the goal of our pitch control is to align the blades to find the optimal angle for rotation. Using this, we attached 3 servos to our center shaft. These servos will pull on certain rods to adjust the pitch of the blades. Each blade will be able to adjust between 40 degrees. On the next slide, we have a demonstration of that control.
So in this demo, we're simulating input from our sensors, and the video is just showing that each of the blades are able to act independently to capture the wind when it's in that environment.
So our group has 3 loose ends to tie up. We have to clean up the wiring, ensure all electrical components are inside the water-resistant control box. We have to remachine the blades ends. Right now, currently it's 3D printed plastics, and we want to change that to an aluminum material. And then we have to finalize our control code. For the future of this project, we would like to implement it into real-world environment, which will be a barge off the Baltimore Harbor to get full wind testing and full environment testing. We also want to attach a load to the generator so we can charge a battery. And then we also want to make the brake control automatic. Thank you so much for listening to our presentation. We hope to see you in the hallway.
Can you talk about your so it's being designed for an external environment, right? Can you talk about the decisions you made in terms of material or finishing to make sure that your build is actually going to be able to withstand those environmental conditions?
Yeah, so we came into this project while all those factors were already decided by Dr. Yu and his group and the Blue and Green Energy Solutions. So our role was mainly to assemble the turbine, do testing on it, and make sure everything works up to their standards.
To piggyback on that, the material was chosen for corrosive environments. So I believe it's cast iron, steel for, yeah. Okay, right? And then also we have plastic materials between our metals to ensure the corrosion doesn't happen on that metal-metal contact.
So what were so besides assembling it, what were the innovations you made? Was it in the controls or?
Yeah, so we, the sensors that they were decided by Dr. Yu, but our role was to take the sensors, make it work, make all of them work, have them on the turbine physically, and then implement code. We were given an equation by Dr. Yu that determines the angle of the blades. It's a function of wind speed, direction, and then turbine speed and position. So our job was really to take the sensors, take the value from them to a unit that we need and plug it into that equation to actuate the blades and to implement it all to work.
Congratulations, thank you all. Google Slides or presentation? Google Slides? Slides, okay. Thanks. Here's slide. Okay, and then yeah, it's this one, right?
Good afternoon, everyone. This is the Smart Treadmill Capstone team. That's David Ulufade. On the far left, that's Michael Zambri, yours truly, Nkosi Cruikshank, Nick Myers, and Yadel Durese. And we're going to go through the progress of our project thus far.
Hello, everyone. First, I'd like to begin with what is a smart treadmill. Our stakeholder, Dr. Goker, the program manager of the engineering management program here at UMBC, would like us to create a treadmill that is capable of autonomous variable speed control based on the runner's input. Here on the slide, you'll see a very simple system boundary diagram consisting of the smart treadmill in the center, a runner as input, as well as our 120 volts AC signal. Next, I'd like to move into our system requirements. The treadmill shall be able to adjust the speed based on the runner's behavior through a sensor system. This is implemented through an array of 5 ultrasonic sensors. The treadmill shall also have an emergency stop mechanism. This is to ensure the safety of the runner, and it is implemented through a safety tether. The treadmill shall have 3 defined zones. The first is the acceleration zone, the middle is the active running zone, and the end is the deceleration zone. What we're calling our custom control unit, or CCU, shall use the lateral position of the runner to increase or decrease the motor speed proportionally using a proportional integral derivative control loop. Next, I'd like to move into our design description, starting with our system architecture. Here in the center, you'll see our Arduino Mega, which is acting as our custom control unit. It interfaces with our array of ultrasonic sensors as well as our Hall effect sensor to measure the speed of, or the actual speed of the motor. It's also sending a pulse width modulation signal to the treadmill's control board, which in turn controls the motor. In addition, we have our human-machine interface, which consists of a Raspberry Pi and a display.
Hello, my name is David Lufade. I'm going over the software design. So in our design, we have 5 ultrasonic sensors that we're using to detect the position of the runner. So if the runner is in the upper half of the treadmill, they're in the acceleration zone, speeding up the treadmill. If they're in the lower half of the treadmill, they're in the deceleration zone and slow down the treadmill. In the middle, we have the active running zone, where we can remain the speed of the treadmill, make sure the person is staying the same speed. And depending on this area, we will have the set point change depending on where the position of the runner is. And from there, we're going to measure the real speed of the treadmill using our real Hall effect sensor. And this will measure the real speed in RPMs. And from there, we're going to adjust the speed of the treadmill using a PID control loop. And here, we use a weighted array of sensors, with the highest priority being in the middle, and the outer end being the lowest priority for our sensors. And here, just showing our GUI design. So provided start signal, the treadmill will start, and we have a stop functionality to stop the treadmill. It will give the user the elapsed time they've been on the treadmill, the distance they have run, and the speed of the treadmill.
We will now be moving on to the mechanical design aspect of our project. Initially, we started off with having 1 ultrasonic sensor and having the user be able to adjust its height along with where it's placed on the treadmill. And this just enabled ease of access to the user so that it can be used by many users with different heights. We deviated from that idea as having 1 ultrasonic sensor didn't give us an accurate reading of the user's positioning. So we decided to have 5 ultrasonic sensors, and then we placed them equidistant apart from each other, about 21 centimeters apart. And then we realized that the ultrasonic sensors have a plus or minus 30-degree range where they can capture inaccurate data. Therefore, we had to use some trick to figure out what is the best orientation to have them facing. And then in the end, this is what our design looks like. The user can still adjust the height of the sensors so that we usually want it to point directly towards the user's torso and chest area, as that gives you an accurate reading of where the user is on the treadmill. And then here's the design for our HMI housing. This houses our HMI 7-inch HMI panel along with Arduinos and any PCB design that we have, which will be mounted on the back. This is everything put together on our treadmill. As you can see on the outer ends, we added some arm and linkage systems to reduce runner-induced vibrations, as when we were testing our first prototype, we noticed that the far ends had some oscillations, which messed up our reading for ultrasonic sensors. And then you can also, you can also see our switch and emergency switch.
Hi everyone, I'll be going through our testing and evaluation portion. So we started out with an isolated ultrasonic sensor test. We sampled distances from various lengths from the sensor. As you can see, as the distance increases, our margin of error also increases. However, our treadmill is around 120 centimeters long, and within that range, our sensors are 97.3% accurate, which is within our specs. Moving on to our drive motor, we learned that the pulse width modulation, or PWM signal, is what drives our motor at different speeds. Originally, the controller was only capable of 1 mile per hour increments. By plotting these points and performing a linear regression, we were able to find the PWM signals for the intermittent values. So this was a starting point for our PWM calculations. Moving on to our Hall effect sensor. The Hall effect sensor was a part of the original treadmill mechanism and gives us the reading of the real speed of the belt. We noticed after plotting this, the blue line being our findings from the previous slide and the yellow line being the Hall effect sensor readings. We noticed that the readings were off by a consistent factor. So using this plot, we were able to find the exact PWM values to give us more accurate speeds.
Okay, so before I go through the progress this far, one thing to note is that this is a 2-semester capstone, and last semester we actually started out with a budget of $1,000. After purchasing all the necessary parts, we are currently at a budget of $300 remaining. So at the end of last semester, we had a few issues. The first major issue, a setback actually, is that the incline motor stopped working. After speaking with our stakeholder, he deemed it not critical for the project, so we omitted it going forward. Originally, we only had one ultrasonic sensor that we used for the speed control, for the feedback mechanism, and it was only able to increment speeds at 0.5 miles per hour. In February, when we started this semester, we kind of made improvements on that, where we could now increment speeds at 0.1 mile per hour increments. And we started fiddling around with the CAD design for the emergency stop signal. In March, we conducted tests with our 5 ultrasonic sensors to see how well the feedback mechanism works and how the speed control works better. We introduced the weighting system to those 5 ultrasonic sensors, where the center one has the highest priority. And we, of course, did some more work on the emergency stop mechanism. In April, we had another major setback, wherein that we shorted out the 2 PCBs that we used. So we had nothing to do for 1 week because we couldn't physically work on the treadmill because we had to wait for them to order. Meanwhile, we did that. Meanwhile we were waiting, we actually added the vibration damping mechanisms for the extreme ends of the sensor bar. And software-wise, we worked on the PID loop so we could introduce a more smoother transition between the speeds. For May thus far, we worked on the communication system between our Arduino, which is the custom control unit, and the Raspberry Pi, which is what we're using for our custom display unit. We fully implemented the PID control loop, so it works good enough now to our specifications. And we made the validation and verification documents plots based on the data collected from the read sensors. From that, we have more accurate PWM values and have more accurate speed control as a result. And that's the end of our presentation. Do you have any questions? Well, the goal is to, yes, keep them on the treadmill. The center would be the active running zone where there would be no speed control whatsoever. And as you approach the front, it will accelerate so that it will cause the runner to go back to the center. Similarly, if they're at the end of it, the lagging end of it, it will slow down so that they could catch back up to the center. So that center is more or less the set point that we want them to go back to no matter what. It is. You can in detail, but yeah, outside.
I guess further on that is turn it back on. Turn it up. Hello? There you go. So the adjustment speeds, like if someone's like running versus walking, like if it's incrementing, like speeding, like what's the speed up or slow down of the, I guess, treadmill when it's, I guess, reading the run, like if it's runner versus like walking? Is that, I don't know if I'm asked the question.
We don't really differentiate between running and walking, just looking at the location versus speed. So as usual, someone's walking speed might be considered running. Well, not really, but it depends for the individual, if that makes sense.
Yeah, I guess my question is like someone who's walking, I guess the speed to adjust, it'll be easier to kind of like react to. If someone's running and they get like an abrupt stop, is there like some sensitivity to that in your sensors?
Yeah, actually, in our design, we don't. We slowly adjust the speed to like for our set point. So if you were running, you won't automatically just stop unless you have an emergency stop. But if you're walking, for example, you want to go to a faster speed, it will take some time to adjust to that speed. It's not just automatically speed up and slow down. It will take some time with it.
Yeah. So what is? Do you know what is that delay like between the electronic sensors saying, "Hey, okay, this person is going fast," and then the system going through and then actually reducing the speed of that bell or slowing it down?
Yeah, we have a sample rate of about 0.5 seconds. So each time it will sample you, and it will increase the speed or decrease the speed depending on where your positioning is.
All right. Congratulations. Thank you all. And we have about 2 more. Thank you all for bearing with us. Right after this, the students will go outside and set up, and then you can see everything that you saw here actually in person. So if you have more questions, including the audience, this is that opportunity. And did you guys do Google or?
It's on PowerPoint.
Regular PowerPoint, okay. Which one?
I don't think it's open
No,
yet.
no, it's not open. It's not. All right. And so you are.
All the way to the last one.
Yeah, it's the bottom one.
Oh, you're last. Never mind, you did last one?
No,
there's
one more.
2:30. I was going to say, I know I
They
have one
did 2
more.
underscores.
Oh, yeah.
there.
All right, good.
All right.
Oh, you guys didn't go.
They also need a mic.
Yeah, I don't want to talk. All right.
Good afternoon, everyone. We are the attritable UAV team. My name is Aaron Sadowski. This is Jonathan Sardin, and this is Nolan Smith. We are the mechanical engineers.
I am Nick Jones. This is Raymond Kacharik and Matt Dufilly. We are the computer engineers.
So I will start us off by going over the requirements that we had to deliver. We had to prototype a rapidly fielded attritable UAV. Attritable meaning that it's low cost, reusable, and expendable. And rapidly fielded meaning that it can be quickly manufactured using additive manufacturing techniques like 3D printing. It is to be able to deliver a 10-pound payload at 10 nautical miles, and this project is actually a continuation from a previous year's Capstone project, and we are partnered with Northrop Grumman for the project. So after going through the final design, the key specifications for our UAV is that it is a 52 by 52 by 12 inch dimension. It is 28 pounds. That includes the 10-pound payload. It can fly up to 15 nautical miles, which is 5 above the 10 that was required for us. And we calculated that using computational fluid dynamics. As you can see in the graph at different angles, it demonstrates the different distances that the UAV can fly. The UAV is also able to carry the 10-pound payload in a 6 by 6 by 6 box, and it is able to be controlled both manually and autonomously. The materials that we used for the airframe are PETG carbon fiber. As you can see, the red design is the old design that the previous Capstone team had developed, and our new design in the green as us iterating upon that old design, and we will go over the changes that we made throughout this presentation.
All right, I'll be going over the changes made to the landing gear. So last year, the landing gear that they used featured 2 legs that were bolted and mounted flush to the bottom of the central hub. But as a result, from those holes created for the bolts, those were failure points. And as a result, the legs failed very easily and early on in the flight tests. So as a result, we changed to 4 legs that were now going to be inserted and press fit into the hubs. This will allow us to use the strength of the hub to our advantage, hopefully reducing the stress concentrations made from the bolts.
There were 3 critical regions with the arms where the arms failed last year, resulting in multiple crashes. Excuse me. The first 2 were located at the entrance and exit holes of the arms for wiring. As you can see here, there's 2 cracks at the entrance and exit holes where this is the most stress concentration. We validated this through FEA and realized that we needed to fix it moving forward. as well as one additional place of stress concentration at the connection point, as shown here, between the inner and outer arms. As you can see on top, we have our old arm design pointing out the 3 locations where these stress concentrations are currently located. Moving into our new arm design, we have removed the central wiring throughout the arm and rerouted the wires on the outside of the arm. Additionally, we have removed stress concentration at the end of the arm where the motor wires enter the arm, as well as also rounded corners on the entire arm to reduce corners and cusps where stress concentrations can rely. Lastly, at the connection, we fixed the connection between the inner and outer arm utilizing a common 3D printing technique that includes thicker outer walls on the inside of the part to distribute the load through the entire arm and not just the cap. You can see on the right that we statically tested our arms with free weights, dumbbells, and a little bit of paracord to ensure that our new arms fulfill our requirements.
Another change that we made since last year is changing the battery system on the drone. Last year, the team decided to go with 10 smaller 2.6 amp hour batteries, putting them all in parallel to get a total of 26 amp hours. We decided to go for one larger 28 amp hour battery. Even though this one battery is heavier, half a pound heavier than all the other batteries, it gets us a better value as we get more battery capacity per dollar, giving the drone a better value. And we also saw that it improved our maximum flight distance compared to last year's design. And you can also see that the one battery can be mounted on top of the drone with a mount where you can loop through some battery straps, as opposed to last year's design where they had caddies around the outside of the drone to hold all the smaller batteries. This leads to less printing time for the drone, helping us achieve our rapidly fielded requirement.
We conducted FEA using SolidWorks on all the parts of our drone, including the hub, inner and outer arms, as well as the battery mount. Today we'll focus on just the landing gear. So with the FEA results, this is a study done with a static force of 200 pounds, which is well over what we're going to experience in flight and or during landing. But only until then where you'll see those areas of red of high stress and possible failure. These legs were designed to withstand a 10 meter per second or absorb a 10 meter per second crash landing in hopes of protecting all the more important components that reside within the hub. And again, this can support over 4 times the weight of the drone, which is above what was required.
We have a number of radio systems on board. So we have an onboard telemetry radio, manual control radio, as well as live video coming from the drone. One of our concerns was with this carbon fiber filament and how it would attenuate some of our radio signals if they were located within the drone. On the left-hand side, you can see an attenuation plot as a function of material thickness. What we saw was after 1.5 centimeters of material, our signal was attenuated by 3 dB or half power. As a result, all of our radios are located external to the drone, and you can see their mounting locations here on the right. When flying autonomously, we needed to make sure that the drone could avoid obstacles, since the ground operator may not have the most up-to-date terrain data. As this, we equipped the drone with a Lightwear SF45 LiDAR. As you can see on the right-hand side, this can see objects as the drone flies, including a maximum detection range of 50 meters. The horizontal bendy ruler algorithm allows the drone to detect these objects and navigate horizontally to avoid tall, thin objects such as radio towers, which we expect to be the primary object flying around.
For our payload delivery mechanism, we decided to increase the volume of the payload to meet the 10-pound requirement by 116% as opposed to last year's design. We also, of course, have safety redundant mechanisms to ensure that no payload gets dropped when we don't want one to. And we also included a smart payload integration system so that in case you don't want a payload, you can equip some electronic device and control it through the signals you send to the drone. For our timeline, the first thing we did is in September, we split up the work into 2 groups, one for the mechanical engineers and one for the computer engineers. The mechanical engineers were responsible for doing testing on all the arms and legs, while the computer engineers had to integrate all the electronic components that we inherited and the new ones that we bought as well. Other than that, at the end of the year, we combined everything and are doing our final testing.
So our total budget was $2,000. We spent just about all of it. A lot of it was for the new battery and also replacing parts from last year. Go on to the next slide. And over the next few days, we'll be testing some of our system requirements, such as ensuring we have the proper ground speed we need, vertical speed, and also ensuring that the payload functionality is working. Any questions?
Hi, it was a really good presentation. You mentioned early on that you had determined the flight duration based off CFD analysis. Could you go into a little bit more detail about what model was performed to determine total flight time available?
Yeah, so the way we did it was through SolidWorks. We had our CAD in there, and SolidWorks has built-in flow simulation. So from there, we put in different airspeed values and different flight angles and figured out what the drag force was on that. And we also performed static thrust testing with the actual motors to see how much current they draw at different thrust values. Then with both of those pieces of data, we figured out at each flight angle how much thrust do we need to ensure we're compensating for gravity. And then at what airspeed does the horizontal thrust match up with the drag, and that will give us like our estimated flight speed. Then using the current draw, we can figure out how fast the batteries will drain and then figure out how far it'll go with the time and speed.
Thank you.
Logan, you have to have all the questions, because this is like, Logan works at NavAir, so watch out.
I'm not going to be asking
those
questions. No. So since you did take a failure and then change the design, did you guys find any issues with fatigue or overall like lifetime expectancy? Like, was that an issue that was discovered?
We thought that it was best to sort of not worry about that. One, because to actually test and get results, it would take a lot of we would need to print a lot of samples. We didn't have the time or money for that, and also this was designed to be an attritable UAV. So at the end of the day, if it crashes and has a severe landing, and we lose it, then we lose it. That's not something we can really account for.
I'll piggyback on it and clarify your question. Was that with last year's design or our own design?
So I guess like last year's design, you saw that there were some issues and it broke.
Mhm.
And was that caused by fatigue and just overtime of use? And then what did you guys do from that, learning that and building off of it?
Yeah, so we did a failure analysis on the actual drone itself, and after we performed the FEA analysis, we noticed that there was an extreme amount of stress concentration at the hull, and we believe that it was due to a rapid failure, not a failure over an extended period of time, mostly because of how much stress was at the hull, because the motor at the end of the arm provides so much torque at that specific end of the arm, and to include a hole there, it was going to fail way before the actual material failed itself. So by removing that and testing it over and over again statically, as well as moving forward actually on the drone, we expect that issue to disappear.
Thank you.
Thank you.
All right, congratulations. Thanks. Good job. Good job, Carol. Yeah, beautiful. Last but not least, I mean, you guys have done this for how many times? One of you guys do it. I'm not doing it. All right, one more. Thank you again. This is our last presentation of the day. You guys are great. This is, they've been doing this a lot this semester, so our final group, go right ahead.
Good afternoon, everyone. We are the Cloud Seeding Without Burst team. This project was done in collaboration with Lockheed Martin. I'm Ethan. I'm a senior mechanical engineer. I'm joined with
I'm Corey O'Toole, also senior mechanical engineer.
Nush Guy, senior mechanical engineer.
I'm Isaiah Rowan Reed, senior computer science.
I'm Daniel Zamora. I'm a senior computer engineer. Okay, so the whole purpose of the project is to launch rockets where they release environmentally friendly particles across large areas that are experiencing either drought or wildfires. We had some goals to we had some goals that we needed to achieve. Starting off, we had to utilize 3D printing techniques in order to design the shroud. We also needed to make sure that the rocket begins dispersion at an altitude of 200 feet. Now, we also had to make sure that the dispersion system and the recovery system of the rocket are separate from one another. And finally, we had to simulate the dispersion utilizing computers.
I'm Corey again. I'll be going over Design 1, or Typhon V2, which was designed and tested from October all the way up until April. Now, to start, we have the electronics housing. Now, all three designs share the same electronics housing. The electronics housing houses our onboard computer, our portable battery pack, our altimeter, and our servo, which is centered and mounted at the top such that the gear mates with our particle dispersal mechanism. Now we have the particle control volume above that, which houses our particles. Then we have the control volume housing, which goes over our control volume. Now when dispersion is not occurring, the air inlets and particle exits are covered such that no air enters the control volume, as well as no particles leaving the control volume. Now at 200 feet, the particle control volume rotates such that the air inlets align as well as the particle outlets. Now this allows air to enter the system as well as particles to leave the control volume. Finally, we have the conical lid. It's removable, so it serves as an easy way to load the particle control volume with particles, and then it also serves to improve our aerodynamic performance. Now on the left, we have a test flight picture where we were able to confirm dispersion and capture it at a lower altitude. Now we see a rapid rate of dispersion that is somewhat chaotic in nature.
Hi, I'm Ethan. I was responsible for the second design, Cerberus. This was done from February up until April. The main idea of this design was to create a smoother, more uniform flow of particles. And we achieved this through the use of the new air inlet and conical lid, as well as a new barrel particle release volume. When not dispersing particles, the barrel particle release volume is actually blocked off from clips you can't see inside of the control volume. And when the rocket reaches the 200 feet altitude, the holes in the barrel particle release volume open up, allowing air to travel down through the conical inlet, through the center of that barrel particle release volume, and out the outlets on the control volume. This rocket was able to really solve issues with particle clumping when particles were exiting the rocket, and we can see that from the picture on the right. That was another one of the low altitude test flights, and we saw a very smooth, uniform distribution of particles coming from the rocket.
Hi everyone, my name is Nush, and I'll be going over the third design, codenamed Avernus. Avernus was developed largely throughout March and April, and the goal was for it to be the most aerodynamic of the three designs. The idea is if we can reduce drag on the rocket, that we can achieve a greater altitude and therefore maximize our area of dispersal. This was in fact accomplished, as Avernus had a drag coefficient of about half of the previous two designs and went noticeably higher during test flights. Breaking down the 3D model on the left-hand side, first we have the conical lid, a very smooth cone with the air inlet at the very tip of the cone. Next, we have the control volume. The control volume houses the particles, and the exit vents are down here. That is where the particles will disperse from. These are initially blocked by that part on the particle release mechanism. Inside the control volume, we have gaps and blockers. The gaps and blocks, these will be shut by the particle release mechanism top plate to begin with. And upon reaching our desired altitude, the particle release mechanism will rotate such that the gaps on the control volume align with the gaps on the particle release mechanism top plate, therefore allowing the air to flow through and underneath the plate where the particles are being housed. The particles again release from those exit ports upon the servo rotating. And when we see the vents open on the right-hand side, upon a test flight, we do see the particle dispersion clearly on the rocket body and visible dispersion. Corey will now talk about the particle simulation computer modeling.
So once we had multiple test flights, we focused on the particle simulation of each design. This was done through SolidWorks and was a combination of flow simulation as well as particle injection. Now, once we decided upon appropriate conditions such as particle diameter, particle density, as well as appropriate external flow parameters, we had accurate simulation of all three designs. To start with Typhon V2, we saw the most significant rate of particle ejection, but all this circulation in the control volume led to an unsteady flow rate. Now this matches up with the physical test flights we saw, where we saw a significant amount of dispersion, but it was unsteady in nature. Now Cerberus, we saw a much more uniform and steady flow rate. However, when compared to physical test flights, we saw more physical dispersion than we were expecting when looking at the particle simulation. Now with Avernus, we see similar movement in the control volume as the Typhon V2, but it's limited due to the differing dispersal mechanism. We also see a more moderate rate of dispersion. Now this can't be compared to the physical test flights since we were unable to physically capture the dispersion for Avernus.
Hello, my name is Isaiah again. I'll be going over the electronics interfacing. So our main electronics that went on board the rockets during the flight were a Raspberry Pi 02W, a BME 280 altimeter, and a micro steering servo. The primary goal of our project is dispersion, and we facilitated this through a servo that opened the dispersal mechanisms, which were vents on each of the shrouds. To interface with the servo, we attached it to the Raspberry Pi, and I set up a script in the native Raspbian environment to deploy a Wi-Fi hotspot so that I could connect to it, SSH to it, and deploy the script. We set up the script such that the altimeter would record flight data such as the altitude in meters, the pressure, and the time. Here we have the software organization. We set it up such that there's an initial setup where we do boilerplate import statements. We also set up objects for each of the devices, and then we get into the main script. We have a check for the minimum altitude, which was 200 feet, and then we begin dispersion. We set it for a time period of 5 seconds, and we poll for data every 10 seconds until dispersion is complete. Lastly, I would like to mention that of the $2,500 budget we were allotted, we have spent $1,500, and I'd like to open it up for questions.
So am I correct that the outer casing, including the cone, is all 3D printed? Or
yes.
Did you explore any post-surface treatments to the 3D printed parts to help improve the drag coefficient of these designs?
Not necessarily to improve the drag coefficient, but we did do some post-part processing to reduce friction in the rotating mechanism, just through fine grit sandpaper.
Okay.
Yeah, just to piggyback off that, you're talking about like resurfacing the 3D prints?
Right, just because they have stair-stepping from the layer lines. On
the surface friction on plastic is already low enough that the stair-stepping from the 3D printing wouldn't have an effect on like I think the boundary layers are they're like 1/100th of an inch. So it's large enough that it already covers the stair steps from the 3D prints.
Okay, thank you.
So from my understanding, you guys did the test flights and then ran the SolidWorks simulation model. Can you guys walk through the purpose of doing that?
So we've kind of actually done test flights before and after the simulated model, just because of the amount of test flights we're doing with getting good results, because some days it's too cloudy to see the particles very well. So we've kind of been doing testing throughout, but the simulation was done in end of March, roughly. Yeah.
So the simulation was almost as a validation of the test flight?
Yes, and to
versus-
align the test data that we're collecting with a simulated model.
Okay, thank you.
So since were you shooting these at UMBC?
Oh, no.
Okay. Where exactly?
Friends, fields.
First we were at a local park, and then we moved in Mount Airy, Maryland. We know somebody with a lot of land.
And how high are these going again?
It's topping out at like 600 or 700 feet.
Okay.
Depends on which design it is.
Yeah, I was just curious if there was any FAA regulations you had to abide by.
So that's why we
since
couldn't shoot them here.
Okay.
There's we got in contact with the NAR, National Association of Rocketry, and they told us that we will break the DC no-fly zone flight ceiling.
That makes sense. Yeah.
So did you pick up from a previous project? Okay.
This was done from scratch.
Okay, brand new project. Okay. So I appreciate that you really went in depth in showing how you resolve the problem in terms of particle distribution problem. Could you talk about the other design characteristics of your vehicle as a whole? And I don't know, maybe you did talk about it in the previous fall. I don't know if you did, but could you talk about it slightly? Just
I'm not sure what you mean.
like what are the other, so you went over the particle distribution deployment section, right? But what are the other sections of your vehicle as a whole? And
The particle distribution portion, like the mechanism, that's the shrouds. That's all we were responsible for, if that's what you mean.
Okay.
Yeah.
Okay, I wasn't sure. So the rest of the vehicle wasn't really part of your scope?
No, the rocket body was. We bought a bulk pack off of Amazon.
Okay, all right. That wasn't clear. Thank you.
All right, congratulations.
Thank you.
That was our last presentation of the day. We ask that you let the students, you may go up and go out to your tables now, and we'll give them a few minutes. Thank you all. Thank you, Dr. Von Lockett and Dr. LaBerge, who are here, and the other faculty. And next we have our demos. And so have a great, wonderful day online. Thank you for joining us, and have a wonderful day.